keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian dan peternakan, kesehatan dan farmasi, material maju, energi, teknologi, informasi dan komunikasi, pertahanan dan keamanan, dinamika sosial, kemanusiaan dan kebudayaan, kebencanaan, inovasi teknologi dan pendayagunaan iptek, pelayanan, pengujian, dan pembinaan ilmiah, serta peningkatan kualitas SDM iptek. Kerjasama keilmuan LIPI dalam negeri meliputi kerjasama penelitian, lisensi teknologi, pengembangan, aplikasi dan komersialisasi hasil penelitian, kerjasama non-penelitian, dan konsultasi kepakaran LIPI. Sedangkan kerjasama luar negeri, LIPI melakukan joint research, workshop, pertukaran peneliti dan beasiswa mancanegara, selain aktif menjadi anggota dan focal point di berbagai organisasi internasional. Melalui kolaborasi bersinergi, menghasilkan riset yang berkualitas, LIPI terus memberikan manfaat nyata, kontribusi berarti, dan turut mewujudkan cita dan asa membangun negeri kita tercinta, Indonesia. Indonesia merupakan negara yang kaya akan sumber daya alam. Salah satu aset yang kita miliki adalah kekayaan mineral. Pusat 1965 yang disertai berbagai perubahan nama dan struktur organisasi hingga saat ini. Pusat Penelitian Metalurgi dan Material LIPI memiliki 4 kelompok penelitian yang berfokus pada pengembangan baja unggul nasional berbasis biji laterit. Penelitian ini bertujuan menopang kemandirian industri baja nasional sehingga mampu berkompetisi di pasar baja unggul global. Pengembangan produksi baja unggul ini memanfaatkan mineral laterit yang banyak terkandung di Indonesia. Pengembangan material untuk implan medis dan alat medis. Penelitian ini berlandaskan atas kebutuhan akan material implan yang sangat besar di Indonesia. Di sisi lain, selama ini implan disuplai oleh produk luar negeri yang relatif mahal. Penelitian ini hadir untuk menjawab tantangan terhadap ketersediaan produk implan generik yang ekonomis bagi penduduk Indonesia. Pengembangan teknologi pengolahan dan peningkatan nilai tambah mineral nikel, kasiterit, dan magnesium karbonat. Salah satu penelitian dalam kelompok ini berfokus pada riset mineral dolomit yang dapat dijadikan sebagai produk magnesium karbonat untuk aplikasi pada industri farmasi dan kertas. Riset lainnya yaitu pengolahan mineral kasiterit untuk senyawa kimia timah. Pengembangan material untuk industri energi. Penelitian ini dilakukan untuk mencari material pengganti industri energi, meningkatkan nilai kompetitif dari produk, dan menunjang pertumbuhan ekonomi. Bentuk layanan kami bagi masyarakat berupa diseminasi dan kerjasama ilmiah, melalui training dan workshop, jasa uji kimia, uji mekanik, uji korosi, serta analisa kerusakan material. Dengan dukungan SDM yang profesional, Pusat Penelitian Metalurgi dan Material LIPI berkomitmen mendukung peningkatan kemandirian dan daya saing ekonomi bangsa melalui penelitian dan pengembangan teknologi metalurgi dan material berbasiskan sumber daya alam lokal. Karena komitmen kami mendukung kearifan lokal untuk Indonesia yang mandiri. Berawal dari cita dan asa untuk membangun negeri, memberikan segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif, dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung Iptek di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka konservasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia, infrastruktur riset strategis, dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi.
Assalamualaikum warahmatullahi wabarakatuh. Good morning and welcome to day two of the fourth International Seminar on Metallurgy and Materials 2020, hosts, hosts by the Indonesian Institute of Sciences, LIPI. Before we begin, I would like to convey our deepest gratitude to the invited speakers and all participants. Welcome and thank you for joining in. Ladies and gentlemen, the national anthem of Republic of Indonesia. Thank you. Ladies and gentlemen, before we proceed, there are several notes. Again, just like day one, all participants should fill in the attendance list of the seminar. Please do so with the link provided by the committee. And for day two of the seminar, just like day one, there are three keynote speakers that will be that will deliver their topics. The first one is Professor Pyongwil Hwang, and the second one is Professor Hirofumi Tanaka, and the second one is Professor Ana Zulfia Shahrial. And we will begin shortly the presentations from all the speakers. Ladies and gentlemen, all participants, please enjoy the seminar on day two. Thank you.
Okay, thank you very much, the MC, for the opportunity. Assalamualaikum warahmatullahi wabarakatuh, and welcome, ladies and gentlemen, to the second day of this international seminar. Please, the honorable keynote speakers, Professor Byung-il Huang. Hello. And
Hello, hi,
hi.
nice to meet you.
And also welcome our keynote speaker from Kyushu University, Professor Dr. Hirofumi Tanaka.
Hai.
Hello.
Halo.
Yeah. Hello.
Selamat pagi.
And also we will have also from Professor Dr. Ana Zulfia Shahrial, but he is not joined yet. Maybe I will wait later, but we will start. Okay, my name is Dr. Nana Darsono, and it's a pleasure to welcome you all to the fourth international seminar on metallurgy and material from now until maybe I will guide you for this plenary session until 10:40. We will have discussion, and then for the first keynote speaker, we will hear from Professor Byung-Il Hwang, and the topic is about the interconnect for the flexible wearable electronic. But before we go for the first presentation, I will introduce you the CV of the professor, our guest speaker. Maybe I will share screen. Okay. This is the Professor Byung-Il Hwang. Now is the assistant professor of the School of Integrative Engineering, Chung-Ang University, Seoul, South Korea, and he got the PhD from the Graduate School of US Korea Advanced Institute of Science and Technology from Daejeon, Korea, and also from the Advanced Material Science and Engineering, Sungkyunkwan University. And he works from 2060 until 2090 principal research sciences, and then also the industrial practicing from BASF. And he also have an interesting in the mechanical properties and the formation behavior of nanoscale materials, flexible, stretchable, transparent electrodes, conductive polymer composite with the metal matrix particle nanowire, flexible electronic component, and conductive textile fabrication and characterization. He has high index 20 high index with more than 500 citation. I got this from your Scopus, sir. And so almost 37 paper have been published. So in order to sort our time, because this is the Friday in Indonesia, Friday is a short day, sir. So maybe we will start for your presentation. So the first presentation is for Professor Byung-Il Hwang. So the time and the screen is yours. Maybe you can start now, Professor.
Yeah, so can you see my screen?
Okay.
There? Okay, so now I will start my presentation. Okay, so nice to meet you. My name is Byung-Il Hwang, as introduced by Dr. Nono. And I'm an assistant professor at Chung-Ang University in South Korea. And first of all, it's my honor to give this presentation in this wonderful conference. And next time, I really hope you can meet in offline conference and have a little bit more deeper interaction together. So yeah, so I will start my presentation. So my presentation title for today is Interconnect for Flexible or Wearable Electronics. And mainly, I will give my previous research about the silver nanowire based transparent electrode. Yeah, so so before starting my presentation, I would like to briefly introduce about my university, the Chung-Ang University. So Chung-Ang University is located in the center of Seoul, and the Seoul is the capital city of the South Korea. And the symbol of Chung-Ang University is a blue dragon. So you can see this, can you see this cursor, mouse cursor? Okay, so the Chung-Ang University symbol is a blue dragon. So you can see this sculpture, blue dragon sculpture, if you have chance to visit Chung-Ang University. So you have nearly 30,000 undergraduate students and about the 5,300 graduate students. So our university is ranked within top 10 in South Korea. So actually our campus is quite beautiful. So I hope we'll have a chance to invite you to Chung-Ang University later. So, okay, so this is the short introduction of my university. So I will continue my real presentation. Okay, so here are the contents of my presentation. First, I will briefly introduce this silver nanowire-based electrode for the flexible or wearable electronics. Then I will explain the sample preparation method and concept of this deformation testing, which is one of the main theme of my research. And then I will show you the result of the such deformation result. And this part also introduced about this silver nanowire networks under bending fatigue, especially for the deformation reliability of the silver nanowire electrodes. And after that, I also dealing with this kind of algeo layer deposition on the enhancement of the mechanical property and also chemical resistance of silver nanowire electrodes. So this kind of content will be taken in this slide, in this presentation. Okay, so this is first my chapter slide. Okay, so I'd like to first highlight the increasing market size of the wearable or flexible electronics. So according to the market forecast, the wearable and flexible electronics market size will be about this 37.10 billion in this 2020, and the size will be increasing 15.9% every year. So the wearable and flexible electronics are definitely considered as a mainstream of post-smartphone business. So what this means, so up to now, most of the electronics market is governed by this smartphone business. But after this smartphone business era, then we will meet this kind of wearable electronic devices, and really this kind of market size is growing so fastly. So in the technical point of view, the wearable and electronic devices are mostly dominated by wrist or the eyewear. So you can easily see this kind of a band or watch or this kind of glasses. But the technological trend will go to more human-friendly systems, such as this kind of clothing. So for this kind of realization of the real types of flexible or wearable electric devices, the development of the reliable and flexible or stretchable interconnects are really important. So that's why I am focusing on the fabricating this kind of flexible or stretchable electrodes for this kind of wearable devices. But there are actually a lot of different concepts or the different types of material for this kind of flexible or stretchable interconnect. But today I mainly focus on the silver nanowire, which is one of the most interesting material for the kind of flexible wearable electric devices. Okay, so I just want to show you some of the history of this kind of silver nanowire electrode. So before silver nanowire electrode, the indium tin oxide is one of the most widely used material for the flexible transfer electrode of the electronic devices. But it has several limitations for application to the flexible electronics, such as the scarcity and high cost of indium, and intrinsic brittleness that result in the brittle fracture under bending. So under the small strain, this kind of ITO show this kind of crack. So it's really difficult to use for the flexible electric devices. And also to get the high conductivity of this ITO indium tin oxide film, we have to do this high processing temperature. So this is also unsuitable for polymeric substrate, which is the main material for the flexible electric devices. So that's why we need to develop the alternative of this ITO. So therefore, the research to develop a new material to replace this indium tin oxide is currently underway. the potential candidates that overcome the limitations of indium oxide include the metal nanowires. This is the metal nanowires. And also the carbon nanotube or the graphene. And among this kind of candidate, the silver nanowire networks, yes. Silver nanowire network is especially promising compared to the other this kind of carbon-based materials because of its high conductivity and also high mechanical flexibility. So this graph presents the solar photon transmittance versus sheet resistance. This black dot are silver nanowire, and this is silver nanowires, and this is the red dot is the indium oxide, and this triangle is a carbon nanotube. And as you can see, silver nanowires shows the higher conductivity compared to this kind of carbon-based material. So that's why so many researchers is trying to develop this flexible electrode using these silver nanowires. Okay, so recognizing the importance of the reliability of the silver nano network, so several studies are reported. For example, in the case of this left-hand side, so they performed the bending test by changing a bending angle, and they show the increasing sheet resistance upon a bending. And the right-hand side, they performed the cyclic bending test, but in that case, there were no resistance change upon bending. So as you can see, in these works, there are limitations such as the low cycle non-uniformity bending and ex situ resistance measurements. So, and those limitations may cause a different conclusion. So that's why we have to do some kind of new types of testing for the flexibility of silver nanowire electrodes. So in this study, we try this kind of cyclic bending pattern test. So this is the bending machine we used for this testing. So this bending pattern test can induce the uniform bending strain within the bending cycle more than 500,000 cycles. And in addition, the resistance change can be monitored in situ that enable us to analyze the deformation mechanism more systematically. So furthermore, by performing this kind of microstructural analysis, we confirm that this deformation mechanism of the silver nano networks under bending. Okay, so I will explain this sample purification process. So we synthesize silver nanowire by ourselves by using the modified Fourier process. So in our process, we apply this kind of potassium bromide, and we change this silver chloride to this sodium chloride. Then we can obtain the higher silver nanowires, the thinner and longer silver nanowire compared to this original synthesizing process. So we can get this this kind of silver nanowires, and we use these silver nanowires for our testings. So the synthesized silver nanowire solution was spread onto the substrate. So we use the polyimide substrate as your main substrate, and so actually, so our spray system using this kind of electrostatic forces. So this kind of spray system has several advantages, such as the quick and easy and large scale deposition, and as well as higher yield compared to this air spray method, so which means the cost effectiveness. So after this kind of deposition, so post annealing was performed to remove this the PVP layers, so which is encapsulating as deposited silver nanowires. So usually the edge synthesized silver nanowires is encapsulated with this very thin polyvinyl propylene layers. And this kind of PVP layer can cause the higher junction resistance, which is the decrease the conductivity of silver nanowire. That's why we have to remove this kind of PVP layer. So this kind of removal of PVP layer can be achieved by this post-annealing process. So after this post-annealing process, we can increase this resistance more than double. Okay, so this is the concept of our bending fatigue tester. There are two plates on the upper and lower part, and the sample is fixed within this two plate by using this kind of screw. So the contact is made at this two end. So there is the metal contact. Therefore, the resistance can be measured in situ during this cycling bending test. And with it, with the repeated motion of this lower plate, the uniform cyclic bending can be imported to these samples. So strain can be modified by changing the gap. So if we decrease the gap, then strain also can be increased. And if we increase the gap, then strain will be decreased. So the strain can be calculated this equation. So the film thickness is the one of the major factor for determining this strain. Also the radius, which is corresponding to the gap of this two plate, is also the other major factor for determining the strain. So we change the strain from this 1 to 4%. So maybe you can see this value of this number, then you will think this strain is not too big, but this strain value is quite large because this radius of this testing condition only 3.1 millimeter. So usually people use this kind of a 6.3 millimeter for the reliability test of the flexible devices, such as the foldable smartphone, the kind of a Galaxy Fold. So our testing condition is a quite severe condition. Okay, so let's discuss about this result. So these are the results in terms of fractional resistance increase, which represented as the R minus the R0 is the initial resistance. R is the resistance measured in situ during the cyclic bending. So this R minus R0 over this R0 means the fraction of the resistance increase during this cycling test. So this x-axis represents the cycle number of the bending, and this y-axis means the normalized resistance. And this is the result of the silver nanowire networks, and this is the result of the silver thin film results. So as you can see in this right-hand side, the silver nanowire network show the significantly lower increase in fractional resistance than this silver nanowire thin film. In the case of silver nanowire networks, they only show the less than 20%, even at this 4% strain at this 500,000 cycles. But in the case of silver thin film, they showed about this 80% of increase at this only 1% strain. So from this result, we can see the silver nanowire has the really nice mechanical flexibility. So this is can be confirmed as the silver nanowire is the promising material for the flexible and wearable electronic devices. So the reason for the kind of higher mechanical flexibility can be considered as the two factors. The first, the network geometry of the silver nanowire network is able to accommodate the bending without imposing heavy strain on the networks. So if we have this kind of network structure, then we can simply stretch out this structure easier than this the more denser structure of networks. So this is the simulation works on the stretchability dependence of nanowire networks on the density of the nanowires. So as you can see, the smaller density of nanowires show the better stretchability. So what this means? So smaller density will have the more space that can accommodate this bending strain. Then they can have the better stretchability. So therefore, while the metal thin film is confined to the substrate with 100% area coverage, the silver nanowire over 65% of area coverage can efficiently accommodate the bending. So the other reason for this enhanced mechanical flexibility of silver nanowire is the lack of dislocation. So the lack of dislocation interaction within the nanowire is supposed to be the curve for the enhanced reliability too. So fatigue failure of this thin film is known to be caused by the dislocation interaction at the interface between the thin film and substrate. During the bending fatigue, the void or protrusion can be formed by this dislocation interaction, and the formed void or protrusion act as a stress concentration site. So here the stress can be concentrated, and this kind of stress concentration can be result in the fatigue failures. On the other hand, the dislocation nucleation itself is also difficult in the nanowires, and any nucleated dislocation can easily escape to the surface due to the dislocation starvation effect. Therefore, so what this means? So because the silver nanowire is almost a defect-free straight, so to deform this kind of silver nanowire, they have to initiate this new dislocation in the surface of this nanowires. And even though there is the new dislocation initiation, that the dislocation can easily escape to the surface of the nanowires, so they can be again become this the dislocation starvation state again. So this kind of dislocation starvation theory can enhance the strength of these nanowires. So therefore, occurring this dislocation within this nanowire is difficult. Then result in the excellent fatigue resistance. So these two factors can be considered as the main reason for the enhanced mechanical flexibility of this silver nanowire electrodes. But anyway, there were increase in resistance in the nanowire networks during this fatigue test, and it means the fatigue failure occurred in the nanowires. And that's why we tested this microstructure analysis to confirm the reason for the kind of resistance increase in the silver nanowire networks under bending fatigues. So we can see that kind of failures of the silver nanowire networks during bending was mainly due to the failure near the locked-in junction of silver nanowires. So this is this series of scanning electron microscope images taken at the nanowire networks after different bending cycles. And since as the silver nanowires is encapsulated by PVP layer, as I previously explained, and the layer caused high junction resistance. So as we already explained, the thermal annealing step is required to remove the kind of PVP layers. But during the kind of a thermal annealing process, this kind of a locked-in junction was formed, and this junction acted as a stress concentration site. So usually the kind of failure during this bending fatigue is occur this kind of locked-in junction due to the kind of stress concentration. So this junction will be formed by this two different silver nanowires. I mean, two different individual silver nanowires, and grain boundary must be exit at this kind of locked-in junction. So this kind of grain boundary can be acted as a stress concentration site. So as you can see in this kind of a failure, the failure of silver nanowire networks during this kind of bending fatigue test was formed near this kind of locked-in junction. So therefore, we confirm that the deformation mechanism of silver nano networks under this kind of bending fatigue, which is mainly from this kind of rock-joint junction. Okay, so now I will show you the another the research result of this effect of the reduced graphene oxide layer deposition on the deformation behavior of silver nano networks on the bendings. One of the limitations of a silver nanowire is the low chemical resistance. So because silver nanowires usually have this kind of a one-dimensional structure, so the silver nanowire usually have the really high surface to volume ratio. So because of this kind of high surface to volume ratio, the silver nanowires can be easily oxidized when exposed to the ambient air. So this is the one of the example. So if we expose the silver nano networks in the ambient air, it's kind of oxidized. This kind of oxidation can be formed on the silver nano surface, and this oxidation causes this degradation of the electrical property of the silver nano networks. So that's why we have to enhance this kind of chemical resistance of silver nanowires. And one of the main how can I say, the main concept of the enhancing this silver nano networks chemical resistance is the covering the silver nanowire with this overcoating. So usually people use this overcoating material with this polymeric resin, but kind of polymer-based material usually degrades the electrical property of the silver nano networks and also limits the application of the silver nano networks. That's why we have to use the conductive types of flexible overcoating materials. And graphene is the one of the mainstream for that kind of overcoating material, because graphene has the high conductivity as well as the high mechanical flexibility. So actually, if we use freestanding graphene for this kind of overcoating layer, the property will be better. But controlling the kind of freestanding graphene in a large scale is not so easy. So we use this kind of reduced graphene oxide. So we making this actually recently we can simply buy this kind of reduced graphene oxide from this some commercial market. So for example, Sigma Aldrich. But in that time, at the moment, we use this kind of reduction process. So we buy this kind of commercially available graphene oxide solution, and then we did this kind of reduction process using this hydrogen. Then we can make this kind of reduced graphene oxide plaque in the solution, which has the concentration of the 500 or 600 micrometer per liter. So once we got this kind of reduced graphene oxide solution, we can simply cut this kind of reduced graphene oxide on top of this silver nano electrode by using this same the spray system as the silver nanowire coatings. Okay, so this is the mechanical stability test result of this reduced graphene oxide silver nanowire. Sorry, this is the chemical. This is the chemical resistance test result of the silver nano electrode and also RGO, reduced graphene oxide coated electrode, and this is the mechanical flexible test of the both samples. So as you can see from this result, this blue line is the silver nano networks. So as you can see, the silver nano network without this reduced graphene oxide overcoating show the rapid increase in sheet resistance when exposed to the ambient air for this about the 130 hours. However, the reduced graphene oxide coated silver nano network showed the almost no increase in sheet resistance even after this 130 hours. So you can see from these results, this reduced graphene oxide is really increased this chemical resistance of the silver nano network. And also, if we adopt this kind of reduced graphene oxide on top of the silver nano networks, the mechanical flexibility also slightly enhanced. So as you can see, this black line is the reduced graphene oxide coated silver nanowire networks, and this is the silver nano networks without any overcoating layers. You can see the fractional resistance increase was lower for this reduced graphene oxide coated silver nano networks compared to this only silver nanowire networks. So from this result, we confirm that this reduced graphene oxide would be this really nice material for enhancing this chemical resistance and also mechanical flexibility of the silver nanowire electrode. So this is the scanning electron microscope image of this silver nano networks and also reduced graphene oxide coated silver nano networks when exposed to the ambient air as a function of the exposure time. You can see after 24 hours, there is the almost no oxidation on both samples, but after 60 hours, you can see a lot of oxidation is occurs in the silver nanowire electrode. But with the graphene oxide coating, there are no that kind of oxidation. And after 132 hours of exporting, you can see it's a more severe oxidation of this silver nanowire electrode. But in the graphene oxide coating layer, we cannot see no significant the oxidation on top of the silver nanowire electrode. So this is the ADAX result. You can see we just confirmed that kind of oxidized particles consist of silver and oxide. So that kind of oxidation is the have the composition of the silver oxide. So from this ADAX result. Okay, so this is the last slide of my presentation. So from this kind of mechanical flexibility test of the silver nanowire electrode, we can confirm that the silver nanowire electrode is the promising material for the flexible electronic devices. And also we confirm that the failure mechanism of the silver nanowire electrode. So from the kind of result, we also know that this, if we reduce this kind of locked-in junction on the silver nanowire networks, then we can also increase the, we can further increase this kind of mechanical flux of the silver nanowire electrode. And also we confirm this reduced graphene oxide can enhance the chemical resistance and also mechanical flexibility of silver nanowire electrode further. So the limitations of silver nanowire electrode is the lower chemical resistance, but the kind of limitation can be overcome by this reduced graphene oxide. That things we confirm from this our the experiment. So this is the my last slide, and thank you for your attention. And please let me know you have if you have any question on my research. Okay, so thank you very much.
Thank you, Prof. Huang, for the nice presentation. And maybe you just have to wait for a moment. We will hear the next Q&A speaker. It's okay. And the presentation next will be conducted by our next. Maybe
Okay,
now you can stop
so
your share screen.
if you have no question, then
Okay, we
I
will
will
have
give
a
this presenter
discussion
title
for
to
the
the next
yeah.
presenter.
Yeah. Okay. I will have we will have a discussion
select?
after this two keynote. Maybe you can stop your share screen, sir.
Hello.
Yeah, hello. You can stop your share screen. Hello. Okay. For the next presentation, we will hear from Professor Hirofumi Tanaka. I will briefly introduce the biodata. He currently graduates the professor from Graduate School of Life Science and System Engineering, Kyushu Institute of Technology, and he graduated from the Osaka University, Japan, and from for doctoral, and then for the master from Waseda University, Japan. Maybe I will read the research interest here. He interest in the biomimic electric device, neuroformic electric device using nanomaterials, recently downsizing of electric device or facing physical fabrication limits. To overcome the problem, one of the solutions is to utilize non-human computing. One of the non-human computing is brain computing, which behavior is learning from human brain. So it's very interesting. So maybe let's we hear the presentation for this session. So please, time is yours, Professor. And maybe if you have any question for the participant, please add on the chat on your Zoom. Please put your name, your affiliation, and your question. And for next.
May I?
Okay, yeah, you can.
Okay, today thank you for inviting me such a great conference. So let me thank to organized committee members. Selamat pagi.
Selamat pagi.
Let me share my PowerPoint first. Can you see it?
Oh yeah.
Okay, let me start my talk today. Nice to meet you. My name is Hirofumi Tanaka from Kyushu Institute of Technology, Japan. It's called QTech. And I'm a professor in Department of Human Intelligence Systems. And concurrently, this year, we established the new research center in QTech. And I'm a director of research center for neuromorphic AI hardware, QTech. And this is let me start a point. There's a pointer. Yeah, this is a logo of our research center. So if you know that, I'm happy. So let me start my talk. Today my title of my talk is recent development of neuromorphic AI materials. So let me share our recent result on AI materials. Yeah. So briefly, let me introduce briefly our center. So our center has 4 divisions. So the one is a neuromorphic AI material. So our center aim our center is to develop the AI system from material science side. So we can start from neuromorphic AI material. So based on neuromorphic nature mass model, so that we can develop the system of material intelligence AI system. And if we get good functionality of the electric circuit, we can implement the circuit to the self automatic driven robot like this. So this is our aim to develop developing the system beyond AI system, present AI systems. And let me briefly introduce our university. Our university, QTech, is located in the west side of Japan, Kyushu Island, and the north part of Kyushu Island. We have 3 campuses there, and the Tobata campus is the main campus, and for School of Engineering, and the Izuka campus is second campus for computer science and system engineering. Our campus, third campus, is located in near shore, and Wakamatsu campus. This is for Graduate School of Life Science and System Engineering. And because we are very close to the beach, we frequently have a barbecue party at the seashore. And this is our group members. And he's Dr. Budiman, Faisal Budiman. Now, presently, he's a lecturer in Telkom University in Bandung, Indonesia. QTech is a slightly historical university, and this is the main gate of QTech, and registered as a cultural product of national cultural product already. Because our city, Kitakyushu city, is a modernization of the starting place of modernization of Japan, and you know, samurai in Japan. And that's old style Japanese soldier. And when we abolish the samurai era, it's about 150 or 60 years ago. New government tried to import the engineering technology, high technology from European countries. And this is the first furnace of steel, blast furnace for steel in Japan, located in Kitakyushu city. So this is our first the revolution of technology in Japan. And we can still see the monument of first blast furnace in Kitakyushu city. Now it's taken over by Nippon Steel company now. And now this is because of this history, this blast furnace is registered as a World Heritage from UNESCO in 2015, and you can visit there if you want. Let me move to the introduce of AI system. This is a trend, world trend of research in AI systems, and from material science and circuit and software. Actually, AI system is based on the software presently, and the many big company, GAFAs or Google, Amazon, Facebook, or something, develop a very good AI system in these days. But as you may know, the electric system use high electric power, so we need to reduce the consumption of electric power. So that we are now trying to move back to the circuit or material science for AI system. And as you see here, material science side, there's almost no research is performed for AI system. So this is our target to fill up this part and support AI system in the future. Let me introduce ourselves. So, as a chairman already introduced, I graduated from Waseda University as a bachelor and master, and moved to Osaka University for PhD. And I work for nanoparticle science there. And because I started my research history from metal physics or material physics. And I moved to Riken as a special doctoral researcher, and there I work for nanowire conduction measurement by using double probe STM. And from here, I start from nanoscience or nanoconduction measurement or something. And I moved to Pennsylvania State University, and Professor Paul Weiss, and he's now the professor in UCLA, and the president of Nano Research Center in UCLA. And I started the nano fabrication work there by using a molecular ruler method. And then after coming back from the United States to Japan, I was in the IMS, Institute of Molecular Science, and moved to Osaka University. And around here, I started to reproduce the bio body signals by using materials, and then moved to QTech 2014. Activity around our department. So our department of human intelligence systems. So the research, a lot of research are working for the human brain or related topics for artificial human brain or something like that. Gathered together and working for that. This is a famous robot, a soccer robot developed in our department. And this is a self-recognition auto football player. And won the Japan Cup, Japan Open, 9 years in series. So that they are a very good team. And they can recognize the colleague or enemy or line, goal, or goalkeeper by themselves and think the condition, understand the condition, what is going on by themselves and play soccer. So this is a good AI system. This is another topic, the automatic dream car. Developed in the Kitakyushu City and QTech and Waseda University Kitakyushu campus. And this is also the automatic automatic robot. And this will be driven on the road in Kitakyushu City in the near future. And anyway, so the automatic robots are also required in care, rehabilitation, training, or nursing, in the many other topics, period. Sometimes, but they need a same recognition ability and speed with human. Because, so for example, so if automatic driven car driven on the public road, and if suddenly a ball is coming out from the side of road, and a girl running after the road, ball, if this automatic driven car need 1 second to calculate, to understand the situation, maybe this car will hit the girl. So now we need the high-speed recognition sometimes, like the human brain for automatic robot. And we have a good robotics technology in QTech. And sorry, this is Japanese, but we won the RoboCup World Cup 2017 and 18, 2 years in series by automatic self robotics, servant robot. And we also won the World Robot Challenge 2018 from our department, mainly our department. This is a winning because of the high quality of QTech system. But as I told you, AI software technology will soon be saturated by electric power shortage. Because if such kind of robot increase, so we need a lot of electric power. And maybe the present power plant is not enough for such a kind of robot. So to reduce that main battlefield of AI system, we move to developing hardwares. So that's why we focus for hardwares. Yeah. So this is our dream. Such a picture. This picture is our dream in the future. So we can spend our life together with a robot like this, with no frustration. I mean, now presently the robot is not so smooth like human, but like this, the human robot should behave like a human. That's our target. So stay with the robot for family circle, and in that case, the robot should have behave like a human. So that means the robot must have information data in all emotion categories and answer within the expected range. So if you make a conversation to robot, we have something expectation for reply. So robot should reply inside that such kind of expectation. So to do that, huge amount of computation is required to find the correct solution. So that's why the huge electric power is required. So for example, this is a typical example for power consumption of computers. So this is a human brain, but if you do artificially calculate all function of human brain, we need a supercomputer like this. This is a world fastest supercomputer called the Fugaku computer, developed by Riken and Fujitsu Japan. Now, as you can see, if you use all computer by using all system for computation, we need a 30 or 40 megawatt for calculation. This amount. So for this, we need 1.3 million yen per month. I don't know how much is in Indonesian currency, but it's quite high cost. And we cannot have such kind of a big computer for each humanoid robot. You know, the power plant, the big power plant, water power plant in Japan can make this kind of, this much energy. So if you have 10 human brains, it's almost used up. So it's quite high. So compare from that, our brain consumes only 20 watts for calculation. And the background is 19 watts. So if we focus for something, only 1 watt increase for calculation. So this is very reasonable system as a computer. So that's why we need to develop brain-like processing computer called a neuromorphic computer. So by using this kind of computer, the fast processing with low power consumption is expected. But of course, there's no such kind of system now. So firstly, we can start from brain signal device by using material science. So the more further, I explain why the electric power is required for robotics. So this is a Roomba, not Roomba, but the house sweeping robot and cleaner robot. And in such a amount of size, maybe if this robot clean 2 hours in the house, it's enough. Once a day is enough. And go back to the base and 2-hour charge, it's recovered. It's okay, no problem. But if you use humanoid robot, maybe because of a huge amount of calculation, battery is consumed very soon, like this. And maybe if you use 5 minutes, the battery is charge out, and change to next robot. So if robot go back every 5 minutes and a different robot coming out, can you make a family cycle with such kind of robot? No. Maybe it's not so reasonable. So that's why we need the low power consumption system. So why the brain is low power compared from the present computation systems is like this. So I don't talk detail, but in the moving bias voltage or the process timing, the driving device signal expression calculation method, or wiring structure or information processing, that we can reduce each by each the power consumption this much. So if we can replace from such kind of silicon device to the human brain device, we can perfectly reduce the power consumption of computation. So even hardware had such kind of power consumption problem. So if you have the processing in the CPU or GPU calculation, we need a memory so that we can send a signal to the memory. And if we need information from memory, we can read it. So by transfer of such kind of signal, so that we need a power consumption. And we cannot reduce it anymore. And it's called the von Neumann bottleneck. So the GPU is now using this. So the present AI hardware also has a problem. We cannot reduce power consumption anymore. But if we can use the new style CPU or processor, like in-memory processing or other type of device, then we can overcome such kind of problem. That's why we need to develop brain type materials. So now we can move to the material science side. So we are working for nanoscience, so that we can develop the molecular, we can do the molecular synthesis, and we can cover upstream to downstream of nanoscience. We can do nano fabrication by using synthesized molecules, and then we can measure such kind of nano devices by nano measurement technique. And then if you find a good functionality of the device based on the molecules, and we can develop the specific the devices like this. So the strategy of our the research is, but this is a human brain like this. This is human brain. And we cannot make a human brain by synthesis or chemical synthesis, organic synthesis. But if you make the brain parts by parts, maybe we can develop parts by using such kind of nanotechnology or newly synthesized molecule. So after making such kind of devices, we can combine together and as a brain. So in the future, that we can develop the artificial brain like this. So it's called a neuromorphic device, and move to we can use it as an AI system. Anyway, so we are using the material science, and basically we are use nanocarbon systems and flat planar molecule like this. This is a porphyrin molecule and electron donor. And this is a naphthalene diamide as an electron acceptor. And both molecules can easily attach to the side wall of carbon nanotube because of pi study. So we can control the electric property of that. This is my first research result obtained by nanocarbon system planar molecules. You can see the individual carbon nanotube and porphyrin molecules attached to the side wall of carbon nanotube as nanoparticles. And by measuring each particle conduction by using conduction AFM, we found the conduction of bare no porphyrin area, so its IV become symmetric. And the conduction on the porphyrin particles, so IV become almost same at a negative voltage, but for positive voltage, there's no current, almost no current. That is called a diode because only one direction current passes. So this is the world's smallest diode particle on the side wall of carbon nanotube. It's called at that time, 14 years ago. And it's introduced the Nikkei Nano Business as an important article of the world. And this is the present one, the presently I introduced. And by it's working as a diode, but nanoparticle is working as a diode. And we can also use naphthalene diamide, and we can obtain a similar system together with porphyrin. And conduction system was 4-anode Hamiltonian when porphyrin used. And while it was Schottky emission when naphthalene diamide was used. This difference is just because of the homolomal level difference, because porphyrin is a donor and naphthalene diamide was an acceptor. And this is a different style. So the bundled carbon nanotube used and gold nanoparticle. So the bundled carbon nanotube is always show the metallic conduction. And after putting the gold nanoparticle, this is also metal. The bundled carbon nanotube changed to the semiconductor conduction. So this is a very new finding. So the publishing physical regulators. And this is the single layer graphene nanoribbon used instead of carbon nanotube. Same molecule, naphthalene diamide was used. And in this case, band gap of graphene nanoribbon can be controlled by the number of nanoparticles of naphthalene diamide. So anyway, so by seeing these results, we can know electric property are varied by kinds of absorbed molecule on the side wall of nanocarbon systems. So where we try to use this kind of material for the future AI system. Previously, so Professor Kasaya found this kind of phenomena by using redox active molecule on the side wall of carbon atom. This kind of, especially PMO12 used on the side wall of carbon atom or porphyrin, zinc porphyrin. Redox active means so this kind of molecule always occur redox. So the number of electrons in the molecule is changed frequently. And this is obtained by this device. Only one molecule is attached to the surface of the side wall of carbon atom and measure it. So IT measurement. So you can see the telegraph noise like this. Only two values occurred. So this is because of redox during the measurement. So the only one electron number is changed during higher current and lower current here. And if so, that we thought this kind of redox active molecule can be used as a noise generator. So we tried to develop such kind of system. Presently, we use a POM, polyoxymetallate, for the system on the side of carbon atom. And this system always shows the peak in IB curve. That is called negative differential resistance, because by increasing bias voltage, so current is decreasing. So that's a negative resistance. And this is always this kind of component, NDR component is used for the noise generator in the equipment. So that we thought this kind of material can be used as a noise source of device. And by making such kind of random network with a POM molecule and put the electrode like this, and we measure the current by changing the applied voltage between two electrodes, and start from 0 volt to 125 volt. You can see the amplitude of here current is increased like this. Here amplitude is called as a noise intensity. So by increasing the applied voltage, noise intensity was increased like this until up to 125 volts. So after 150 volt applied, so this stable noise become like this, so unstable like this. We wanted to know what is the source of this instability. So we leave this system for a while. So after that, suddenly such kind of peak pulse was generated in the system. So the previous instability of the current is a source of this kind of pulse generation. And by using the certain condition, the pulse was generated around several 10 milliseconds, which is very close to the human neuron pulse generation. So that's why we thought this kind of system can be used as a spiking neural network, which is used as one of the AI system in the future. And that's why it's published in the Nature Communications. We also simulate the reservoir computing by using such kind of random network. And the reservoir computing is a kind of recurrent neural network, which is another AI system. And this is the reservoir. So the reservoir means that the information is reserved in the system. And the output is the linear combination of electrode signals. And as you can see, the output is linear combination is perfectly following to the supervisors. So we know this random network can be used as a reservoir computer device. And we expect we can use this reservoir system in the future as a time series memory analysis or controlling processing. Anyway, so we now know the carbon nanotube POM system can be used as a reservoir AI system. So that we try to do such a measurement by real devices by using a POM carbon nanotube system. How many minutes I have still have?
You have 10 minutes remain.
Okay, thank you. And this is the real device by using a carbon nanotube system, and we can put such kind of electrode. And this is black paste of random network, and this is the real device for 1, 2, 3, 4, 5, 6, 16 or some electrodes. And we can measure the IV. So the IV show that this system has a non-linearity, not straight, non-linearity of the system. And this also show the such kind of two-state switching or and phase shift also, which means that this system can reserve the information for a while because of delay of information. And this is a requirement of the reservoir computing system. And this is the FFT, and the higher harmonic also observed. This is another requirement for reservoir computing. So that we can know this system can be used, actually used as a reservoir system. And we try the reservoir task. This is a sine wave was input to the one electrode, and the output is another 10 electrodes. And we make a linear combination of that output system. And by making a target as a triangular wave function, and output can be for the target wave like this. And even sawtooth shape and rectangular phase, the wave shape, the output can follow the target wave. So this is the one evidence that we can, this POM carbon nanotube system is a good candidate for the reservoir computing system. And by using this kind of system, that we tried this kind of device, including the random network of POM carbon nanotube to this Toyota human support robot. Or this is a kind of automatic robot, servant robot. And this hand of this robot has a sensor, and by touching this kind of stuffed doll or block or pet bottle, the signal repulsion force of repulsion force can be obtained against the time like this. And by analyzing this, this kind of shape of this function, this robot can be recognized what kind of stuff is grabbed by hand. And we make a linear combination of output 1 and 0 like this. When we try to recognize the block, we can make a block number of output as a 1. And if we touch another, this robot touch another items, it's become 0. And this is actual output data. And when the block is grabbed, it's going to 1, and stuffed door, it's going to 0. And we succeed to recognize block. And in another case, we try to recognize stuffed door, very soft door. And by grabbing a stuffed door, it's going to 1, and the block going to 0. So that we could recognize the block and the stuffed door by using a grab hand through the reservoir system made by POM and carbon. So this is the conclusion of our talk today. So neuron-like electric device by cooperative phenomenon in random network was basically succeeded and published in Nature Communications in 92 years ago. And carbon tube POM network works as a noise generating device and pulse generating device. And various material can be used for a reservoir task, I guess. And this is the first example for molecular device can be used as a computation of AI system and patented 3 years ago in Japan. And this work is published in Nature Communications, as I told you. And after that, many medias, including newspaper or website, introduce our work. Especially website is introducing a lot of website introduce our work, not only in the Japanese, but also English or Chinese website. So we really thank about that. And this article is selected as the most read 50 50 articles published in Nature Communication in 2018. So thank you for many researchers make attention to our work. So this is acknowledgement. So our group has a lot of foreign students, including Indonesian students and other country students, and supported mainly by the Japanese government scholarship called MEX scholarship. So I really thank for the support for the foreign student. Thank you very much. That's all.
Okay, thank you, Professor Tanaka, for your nice presentation. But we will have panel discussion, so we will postpone for the discussion and then wait for Professor Anna here. Hello, Professor Anna. Can you hear me?
Yes.
Okay, welcome, Professor Anna. Sorry,
Welcome.
to sort the time, I will introduce your biography. Sorry, I will share this and okay. Professor Dr. Engineer Anna Zulfia Sahrial is currently a professor of composite materials in the Department of Metallurgy and Materials Engineering at University Indonesia. She joined the department in 1986 after completing her bachelor with the first-class honors degree. She then continued her master and PhD in engineering material, University of Sheffield, UK. With her expertise in composite materials, she was awarded as a full professor at Department of Metallurgical and Material Engineering Faculty of Engineering, University Indonesia in January 28. So to start the time of our presentation and to effective, so you have 35 minutes for presentation, Prof. Anna. So please, time and screen is yours.
Okay, thank you. Moment, please. Okay, can you see my slide?
Okay, we can
Okay,
see the
okay,
slide.
yes. Good morning, everybody. Good morning, ladies and gentlemen. First of all, I would like to thank the chair of the committee here, Dr. Nono Darsono and his team, who have invited me to be a keynote speaker this morning. I'm quite great pleasure to join with your virtual conference. Usually I send my student to this conference, but unfortunately we have the same conference this week, so we only me join with you. So the title of my talk here is Metal Composite and its application, with the subtitle here is Aluminum Matrix Composite, the lightweight for the heavyweight. I'm Anna Zulfia from Department of Metallurgy and Materials, Faculty of Engineering, Universitas Indonesia. So is it a nice environment that we can join with the 4th International Seminar on Metallurgy and Material this morning. So as I know that you are curious, why is the lightweight for the heavyweight? So is it impossible, perhaps, for this kind of work? But it's possible in terms of my opinion, because we do some research, the lightweight for the heavyweight. So let's see in our presentation. So why is metal composite here? So the metal composite now is widely used for any application because of lightweight material. As you know, that lightweight material is quite important material to use for any application, such as in automotive industry, most of lightweight material is the dominant materials, such as the aluminum composite, aluminum composite that we develop. So here, the application of metal composite can be used for the automotive industry, such as brake shoe, the connecting rod, as well as engine block. So the Toyota company in Japan, they have already established this material for their automotive component. But most of developed countries, they have already developed this metal composite for their own automotive industry, but unfortunately in Indonesia, we haven't developed this kind of material. We still use the aluminum and steel material for their automotive industry. Some application of metal composite, they can use for rocket body tube. Some rocket body tube, especially for the small rocket, we can use this metal composite instead of the steel materials, because this metal composite is more lighter than a steel, so they will give a good performance for their rocket. And the other application that metal composite can be used for the space shuttle antenna for our satellite, so we can use this from metal composite. And others application we can use for transportation applications, such as for the train. So some component of trains we can change from the steel materials to lightweight materials, such as metal composite for their brake shoe, for other frame component in the train, or as well in the aircraft. Some aircraft industry, they have a lot of composite materials. Some of them is metal composite. The other application is for the military industry. For the military industry, we need lightweight materials, especially for the military vehicles. So we can reduce the material from steel to metal composite in order to improve their performance. Other application is for the cable transmission. Nowadays, we use the aluminum cable transmission that they have some disadvantages of the aluminum cable because of so ductile. So we can improve this ductility by adding some steel core reinforced. So we call here aluminum steel core conductor. So we can use for this cable transmission. So why is metal matrix composite? Because they have high specific strength, high specific modulus, high fatigue strength, lightweight, the most important thing, that high temperature resistant and high wear resistant. And only a few metallic material that we can use as a metal composite, such as the magnesium, aluminum, titanium. So we select the metal material with low density and ductile. So we can improve the other properties by adding some ceramic particle or ceramic fibers in order to improve their mechanical properties. As you know, that ceramic has good thermal stability, high hardness, high Young modulus, and high strength, so we can combine with the ductility from the metal materials. So the metal materials, we confirm that aluminum is most important metal for making aluminum composite. So in aluminum composite, we combine the aluminum itself with ceramic particles such as silicon carbide. Alumina particle is the most important ceramic that we can use for the reinforced material in our aluminum. So the ceramic here as a reinforced material can contribute to improve the mechanical properties of composite by aura-1 strengthening, grain refine strengthening, as well as dislocation strengthening mechanism. So instead of silicon or alumina itself, so the strength mechanism also come from this mechanism. There are some particles that we can use for the reinforced materials here. We have large particle, medium particle, and nanoparticles. But compare of these particles, so we can use the nanoparticles better, because for nanoparticles, we will have the surface area contact higher than large particles. So that increase the mechanical properties of the materials. But of course, we have some problem to make these materials. What is the problem? In aluminum composite, first is the wetting and chemical reaction between the metallic material and the ceramic materials. Since the metallic material has poor wetting on the ceramic, so we need to modify the melting of the metals. So how to modify them? So we can add some wetting agent. The wetting agent is suitable for the aluminum is magnesium or lithium. So the magnesium and lithium as a wetting agent, then we can promote the wetting between the metallic material and the ceramic materials. And then we also can do the surface coating on the reinforced particles. So we make a coating on the particle reinforced, then the coating will promote the wetting on the liquid metal. So the other problem is distribution particle reinforced. Since the particles tend to agglomerate, so we have to protect this agglomerate by stirrer. So here, the particles mostly have a cluster distribution. So we stir it, then we distribute all of the particles randomly in the liquid metal. And the last is cost production. Therefore, we have to select which manufacturer that's suitable to make the aluminum composite. But in this case, the casting method is the most method to produce the aluminum composite because it's low cost, because the process is simple. And then the process can produce a massive production and low cost. So this is the important thing to make the aluminum composite. So in our research, we have a background of our research. We have funded by the government, from the applied research. So in this finding, we propose to make the breakthrough of the train breakthrough. So it was made by cast iron materials and polymer composite. So in the future, perhaps we have another good material for a breakthrough. As you know, the Ministry of Transportation, they have a target in 2020, the 600 million passenger can hold by the train. So the train can be hold the passenger 600 million a year and 60 million tons of goods. But this year is not finished yet, but we haven't the proven of this data. But according to the Pusdatin of Ministry of Transportation, Pusdatin, it means the data center of information. So we've got the data from the Ministry of Transportation that in 2010, there was 200 million passenger can provide by this transportation. Since you know that transportation is a massive transportation that the people wants to use this public transportation because of first is cheap, faster, and no traffic compared to other public transportation. But what happened in the component of our train transportation? As we know that we have this train, so in this train, we have some component of trains. So the component of train, such as is breakthrough here. So the breakthrough here. Even for the rapid train, we have breakthrough. So the breakthrough mostly made by cast iron. So in the future, we have in Jakarta, we solve the traffic problem by public transportation, that is MRT. They have already conducted 2 years ago, but perhaps at the end of this year, LRT. So what's the component should be applied to this, what's the material of the component should be applied to this train. So we have to consider the durability of the materials. So here we want to make the brake shoe in our research from metal composite. As you know, the brake shoe nowadays use cast iron and polymer composite. So in our train industry, PT KAI, they use this material for brake shoe. But for cast iron, the material is heavy because the weight for one brake shoe is 11 kilogram. But of course, cast iron is a good for strength and stiff. The durability is a month, but cast iron is easy to corrode. And then the cast iron, if they contact brake shoe and the wheel, they produce the blaze. So blaze is quite dangerous for the people. And then the polymer composite is good for the brake shoe because the polymer composite is lightweight. They have a good corrosion resistance, but the disadvantages of this polymer composite, the durability is 2 weeks and easy to tear or break during stop suddenly, because train every kilometer they stop suddenly. So we have a good material. The tough material should be need in this brake shoe. So in the future, perhaps we can develop another material that is metal matrix composite or metal composite. Why is metal composite? Because lightweight, strength, stiff, corrosion, good corrosion resistance, long service life, and easy to fix. So this is the most important properties of metal composite that we can consider for our future application. So in our research, we use the aluminum ADC12. This is actually aluminum 3 series. So the composition of this aluminum, the major is silicon, copper, and iron. So the function of the silicon and copper in the aluminum here, we can see here, the silicon can increase the strength and hardness of the aluminum, improve castability, improve the fluidity of the aluminum cast, and decrease coefficient thermal expansion. So this is good for high temperature. And the disadvantages is poor machinability, according to Rana et al. But the effect of copper here increase the ultimate tensile strength, reduce corrosion resistance, and increase stress corrosion cracking. So this is the disadvantages of copper. Therefore, we can modify the structure of aluminum in order to protect the disadvantage one. So if we analyze the microstructure of the aluminum ADC12, we have this microstructure. So this microstructure actually is affected the mechanical properties of this aluminum. So you can see here, we can find a lot of silicon eutectic in the form of China script, the silicon crystals, silicon free, and some alpha aluminum, the light phase here, and then some phi phase from iron. So if we modify this structure by adding some modifier such as strontium, so we can change the acicular flake to fibrous rod-like. So this acicular flake of silicate, then we can modify to fibrous rod-like. So this fibrous rod-like usually improve the mechanical properties. So according to Ragajanian, the strontium is a good effect to modify the acicular flake of silicon. And then according to Neer et al., they found that the strontium content above 0.12 weight% or between 0.12 weight% to 0.2 weight%. So they produce the intermetallic strontium silicon and intermetallic aluminum silicon strontium. So this reduces the modifier of silicon eutectic. Therefore, they can decrease mechanical properties of aluminum alloy. But this not occur in my research because I use the strontium here is low amount of strontium, less than 0.12 weight% in our research. So in our research, we use the aluminum ADC12 as a composite. Then we use the reinforced material is silicon carbide nanoparticle as well as aluminum nanoparticles. Then we add some modifier, aluminum strontium, grain refiner additive, and magnesium as a promote wetting. So the most important in composite material is the wettability between metallic material and the ceramic materials. So here we have the liquid metal, we have the solid reinforced. So this is the interface. So the interface is playing an important role in composite materials because interface is a medium where the stress or load can be transferred from the matrix to the reinforced. So therefore, we need the liquid metal can wet all of the ceramic during process. So in our research, we have this interface of our composite. We have the matrix, aluminum, we have silicon carbide reinforced, so this is the matrix. So this is a good interface because no fade form in this interface. So when we analyze further with high magnification, there is some reaction product in the interface, such as the spinel, magnesium aluminum oxide, or even magnesium oxide here. So this reaction product also is good. So this is the interface zone. So the interface zone, we can, this is good if we, as we know that the interface zone here is a medium where stress can be transferred. So according to the research that I've got a few years ago, so we do this sessile drop test. So we confirm that the magnesium can promote the wetting because the magnesium can increase the surface energy. The magnesium can reduce the surface tension of liquid aluminum. Then the aluminum can reduce the interfacial energy between solid and liquid. Since you know that surface tension of magnesium is 0.577 Newton per meter, which is less than aluminum. So this element is good for promoting wetting. And also according to Dolata, in their work, they said also the magnesium is a good wetting agent for promoting wetting between aluminum and ceramic reinforced. So how to fabricate the aluminum composite? There are some methods to make aluminum composite. First is stir casting process, squeeze casting process, powder metal, and spray casting. So in this research, I use the stir casting process because the stir casting process has more advantages compared to others process. But in composite materials, the most important is low cost manufacture. So here we use the stir cast process. This is something like schematic of our stir cast apparatus. We have this crucible, we have the stirrer here, then we melt all of the aluminum in the crucible at aluminum temperature, then we pour the reinforced particle into the liquid aluminum, then we mix, we stir it in order to distribute all the particle reinforced in the liquid metal, then we pour into the mold. So, but the most important in this process, we have to use inert atmosphere in order to protect the oxidation between liquid aluminum and oxygen, because in the air we have oxygen. So the oxygen is easy to react with the aluminum. Since aluminum is reactive, so we have to use the inert atmosphere. And then the second, we have to remove all of gas bubble in the liquid metal by degassing. So we also flash the argon into the liquid metal in order to remove all of the bubble. And then we also prevent the gas entrapment during stirring. Then we will have the dispersion of the particles in the liquid aluminum. So in this research, we do this method, stir casting. So for the stir casting, the maximum volume fraction of reinforced, we only can use for less than 0.3 volume fraction. It means there's around less than 30% of volume fraction of reinforced that can add to the liquid aluminum. So this is the research method. First of all, we have to prepare the aluminum block, the magnesium block. We calculate the mass balance of these materials. Then we heat it in the crucible. So in this research, we use various of strontium, start from 0.01 to 0.03 because we use only a small amount of strontium here. And then we use Altip as a grain refiner, and in the same time, in parallel time, we heat these reinforced particles. So in this composite, we use the volume fraction of silicon carbide is 0.03 volume fraction of silicon carbide and alumina. So these particles we heat in the muffle at 1100 degrees C for a few minutes or 30 minutes. Then afterward, we pour into the liquid aluminum. Then we stir it, then we cast it. And after we've got the sample, we characterize out of the sample by metallography, analysis, SEM, EDS, tensile test, hardness, wear test, and so on. So we characterize all the samples. So this is the characteristic apparatus that we have in our lab. So now is the chemical composition of aluminum composite. So since we use the aluminum ADC12, which is the aluminum 3 series, we analyze the composition, the chemical composition by OS, optical emission spectroscopy, that we can find the composition of ADC is here. So the main element is silicon, copper, and iron. And then this is the composition of our composite here. We have the alumina composite, we have the silicon carbide composite. So if we check the composition of those composite, we can see the silicon is not much different, it's close to the matrix one. But the copper, so it's a bit, a little bit different, perhaps because of copper fade in the liquid material, perhaps. So we cannot detect this copper the same as this ADC12. How about the magnesium? The magnesium increase because we add the magnesium as weighting agent 5%, 5 weight percent. So the aluminum increase in the composite here. So it means that the magnesium has soluble in the liquid aluminum. How about the iron? The iron here is close to a bit less than in ADC12. Perhaps some iron has already intermetallic precipitate in the aluminum, and then titanium improved because we use the Altip as much as 0.5% of Altip here, then increase the titanium. So we consider the main element in our composition here, that is silicon, copper, magnesium, iron. So based on this major element, we predict the present in our composite according to the ternary diagram. So this diagram we can search from the Mondolfo. So we have a diagram of aluminum, silicon, copper. So this is the diagram. This is our composition here. So the solidification process, we can see the liquid projection to low temperature, so become solid here. We can find this phase. So the liquid state during solidification become copper, aluminum, precipitate, aluminum, and silicon. But in the ternary aluminum, silicon, iron, we can see our intersection of composition here during solidification. We can see here from high temperature to low temperature, we can see this phase, the iron, silicon, aluminum. Yeah. So in this composition, we have solidify of liquid aluminum to silicon, to iron, silicon, aluminum plus aluminum and silicon. How about the aluminum, silicon, magnesium? Because this is the major element in our composite. So we can see here we have this composition, and then during solidify we have this phase. So the liquid aluminum become magnesium silicate plus aluminum and silicon. So this is actually the most phase present during solidification in our composite. So this is the microstructure analysis. We can see here, we have this microstructure of ADC12. We have this, the gray phase here is aluminum copper. This is the needle-like plate-like is actually the beta phase. This is the needle-like beta phase. This is the light is alpha aluminum. This is the silicon eutectic. This is the silicon 3. How about the microstructure in our composite here? So this is we add the strontium modifier. So the strontium modifier has changed the silicon eutectic become rod-like. So in this composite, we also find the alpha aluminum, the light phase here. So we can see also the silicon eutectic. It means the silicon plus aluminum. Silicon eutectic. We also find the magnesium silicate primary in the form of blocky here. We also find the Chinese script, the magnesium silicate quasi-binary or secondary magnesium silicate. Also, we have the beta aluminum ion silicon. So according to Ragajian also do the same research as ours. So they use the the aluminum 357. So in their aluminum, they add some strontium modifier. They also find the same structure change with the adding of the strontium here. And according to them, the maximum strontium should be 0.03 in order to improve the tensile strength and yield strength. But we will see in our research later. So this is the microstructure of composite. So if we compare between aluminum alumina composite with aluminum silicon carbide composite, we have no much difference between those microstructure. Since we know that in aluminum alumina, we have this Chinese script, we have this silicon eutectic in the form of fibrous here. This is the same as here. Also, we have this is not porosity. This is actually the primary magnesium silicate in the form of blocky, but this porosity. So in our composite, there is no much difference between the aluminum alumina and aluminum silicon carbide in terms of microstructure. So the higher strontium content here, they generate a bit of finer in dendrite structure here. This is the dendrite structure. This is dendrite structure. This is dendrite structure. This is. So we also calculated the secondary dendrite arm spacing. What is secondary dendrite arm spacing? It's actually the distance between secondary dendrite arms. So we calculate from the first arm to the last arm. So this is the distance. So the distance of the arm spacing is S dash. We call S dash, secondary dendrite arm spacing. So we calculate the secondary dendrite arm spacing, then this is the result. So according to my research, the addition of strontium here generate reduce S dash. So the S dash is reduced with higher content of strontium here. But this is for the aluminum silicon carbide. This is the aluminum alumina. So we can see here for the aluminum silicon carbide, we can see the maximum, the minimum S dash here, we can obtain at 0.025 weight% of strontium. So it means the finest S dash generate high mechanical properties. Since strontium here is contribute to dendritic columnar growth in aluminum silicon. Therefore, the S dash reduce. So how about the effect of strontium on magnesium silicate here? As you know, we have this Chinese script structure. Yeah. So the Chinese script structure is not good for mechanical properties because this Chinese script structure can crack nucleation along the interface of this is the interface of quasi-binary magnesium silicate and the alpha aluminum. Therefore, we have to modify the magnesium silicate become rounded or become fibrous rod-like. So this is the addition of strontium is more higher strontium content in our composite. We can see here the magnesium silicate from Chinese script has changed to rounded irregular Chinese script here. So the rounded irregular Chinese script here is improve the mechanical properties of our materials. So when we analyze further by SEM EDS, since we have already predicted our phase using the ternary diagram, that we confirm with ADS, we have the same result as our prediction phase. So we can see here, there is no difference between alumina and aluminum silicon carbide. In aluminum silicon carbide and aluminum alumina, we also find this primary magnesium silicate in the form of blocky here. We also have this alpha aluminum, the light phase. The white phase is beta phase, is content of iron aluminum silicon. We have also Chinese script. This is something like Chinese script. This also we can find here the Chinese script. So the phase present in our composite between ADC alumina and ADC aluminum silicon carbide is not much difference. Therefore, the properties between this composite, I think, is not much different. We will see in our result here. So we analyze the density of these materials. The density of our composite is less than 2.7. Close to the theoretical density is 2.7 of aluminum. So we have less than 2.7 because of porosity content in our composite. So we have this composite porosity of our composite. We can see here the porosity of alumina is less than porosity of the aluminum silicon carbide. How about the mechanical properties of our composite here? We can see here the tensile strength of our composites increase with increasing of strontium addition in our aluminum. So we can see the maximum tensile strength we can obtain at this composition of strontium, which is 0.025% of strontium. How about the elongation? The elongation here, we can see the maximum elongation for the alumina is close to 6% that we can obtain at this strontium composition. How about the impact here? The impact here, we can see the maximum impact strength here we can obtain at 0.025 of strontium. So this is the maximum impact strength of our composite. But the hardness, I think the hardness is similar between aluminum alumina and aluminum silicon carbide. We have the same hardness at this composition, 0.025% of strontium. How about the wear rate? So the wear rate of aluminum silicon carbide is higher than aluminum alumina. It means that aluminum alumina has more wear resistance compared to the aluminum silicon carbide.
You have 5 minutes remains.
Okay. I will finish soon. Hang. So if we compare our composite with the matrix material ADC12, so the mechanical property improve, both tensile strength, elongation, hardness, as well as wear rate, not wear rate. So the wear rate here is lower. Wear rate is lower. It means that our material is more wear resistant. So we compare with others material which is conducted by others authors. So we compare the composite, the mechanical properties of our composite with others author which is conducted by Senet and Bayu. So they conduct this material for their breakthrough, cast iron and aluminum composite. This is my composite. So my composite in terms of strength is higher than their work. Also, the impact strength of our composite is here is higher than cast iron, but close to their composite. And then the wear rate of my composite is higher. It means that my composite is poor for wear resistant compared to cast iron. But the density, this composite is much more lower density. It means that the material is lightweight materials. So this is trend breakthrough material candidate that we still doing the research because we need to analyze further the durability of these materials. So far, the trend company, they use cast iron and polymer composite for their own breakthrough component in their training. So this is actually the polymer composite breakthrough I've got this from Inca. So the breakthrough they've got imported from Australia. So the breakthrough from polymer composite, they don't make this material, but they import it from Australia. This is our trend breakthrough. This is made by our department. We did this last time. So this is not prototype actually. This is close to the original breakthrough where I got the dimension from Inca. So this is our group. We have this lot of students join with our group here. Every semester we have a lot of students, this 10 or 12 students join with my groups here. Last year we visited Inca. We brought all the breakthrough that we made in our department, but Inca very impressive with our work, but unfortunately they don't have such facility to test the durability of our product. So unfortunately our materials are under research. So perhaps in the future. So Inca asked me to discuss with PT KAI whether PT KAI wants to use the metal composite for their breakthrough. Oh yeah, I want to show you this is why the lightweight for the heavyweight. A few years ago in 10-12, I have a research consortium with LAPAN. The project funded by the Ministry of Research and Technology with LAPAN as a leader, consortium leader. So LAPAN asked me to produce the composite tube in order to use for their small rocket RX-122 with the diameter is around 20 centimeter. So in this research, I make this prototype by composite materials. The material is aluminum 6061 with alumina nanoparticles. So the process is simple process, still casting process followed by centrifugal casting in order to have the seamless composite tube. And then LAPAN asked me to enlarge, to grade up the dimension. Unfortunately, I have no equipment to produce the tube for the big size of tube. So I want to join with the company, and then I found the company who produced the Pralon tube. The Pralon tube. Unfortunately, they are not agreed to use their equipment to make this composite tube. So this is the problem. Perhaps if the government give a mediation to the company, so perhaps we can do this for our rocket. So this output of our research has been selected by the Innovation Agency and LIPI to be one of 108 Indonesia innovation in the year of 2006. And 2 months ago, this prototype has been patent granted. So we have a patent of this. So we check all of the composition, we check all the mechanical properties. The mechanical property according to LAPAN is matched for the mechanical for their small rocket. So unfortunately, we don't have the industry to produce this kind of rocket. So now we close with our conclusion here. So the ADC, silicon carbide ADC alumina composite are successful produced by steel casting process. And then the optimal mechanical property was obtained at composite with addition of 0.025% of strontium. And then the dominant phases present in our composite is alpha aluminum, beta phase, magnesium silicate, and aluminum copper. And then we suppose this aluminum composite is a candidate material for trend breakthrough and replace gray cast iron in the future. This is the most important message is aluminum matrix composite offers sufficient promise and have reached the degree of maturity that indicates of their use. To realize their full potential, however, this composite deserves greater attention and support. So this is our acknowledgement to the Ministry of Ministry of Research and Technology and Higher Education under PTUPT grant with contract number, please. Thank you.
Okay, thank you very much, Prof. Anna. Maybe we will have discussion with such a time. Or maybe I will read use a few questions from the chat. This is the question for Professor Tanaka. This is from Permana Andi. So maybe can you hear me? Professor Hirofumi? Yeah.
Yeah.
Okay, this is the question. What are your current constraints in developing the AI and artificial intelligence system to answer the future challenge?
What is the question? So sorry, I couldn't hear you well because of voice.
Okay, what are your current constraints in developing artificial intelligence system to answer the future challenge?
So currently, we are developing the systems which can be used in the autonomous robotics. So there are a lot of good AI system from software side, and as I told you in the presentation, the electric power problem is occurred in these days, and we need a hardware system to decrease the power consumption of systems, and in such a case, to overcome such a problem, we need a newly developed material, not only from the CMOS or other electric circuit presently using the CPU or GPU, that we need to develop another kind of another style of devices for AI systems. That's the purpose.
Oh, okay. Thank you. This is for you, Professor Anna. This is from Muklis from Research Center for Metallurgy. The question is, how about the treatment of the reinforced particle? Is there any pre-treatment for the particle before it mixes with the aluminum matrix? If we use the silicon carbide particles, is there any detrimental reaction such as carbide formation between the aluminum silicon carbide interface? Okay.
Okay, thank you, Pak Nono. Yes, of course. Aluminum and silicon carbide generate the detrimental reaction, such as the aluminum carbide. So we have to protect the aluminum carbide here by treatment of the reinforced materials. So first of all, we can heat this silicon carbide in order to make the silicon oxide on the surface of silicon carbide. So the oxide layer here will react with the aluminum, generate the spinel layer that I discussed previously in our slide. And then the second, we also can make the coating on the surface layer of silicon carbide. So we need some chemical reaction as chemical solution here. Then we do something like electroplating from the chemical solution. Then we mix this reinforced material into the chemical solution. Then we do something like electroplating. Let's say we can use the nitric acid. I think we have this kind of research, but I can see you perhaps next time. I have a lot of data of this, but I cannot tell in this forum because it's too long. The reaction between the chemical solution and the reinforced here, we have proven by XRD, but Muklis, perhaps you can see me in our department. We have this kind of research. I can show you the result of our coating process of the reinforced here. But the easy one is just heat the silicon carbide at 1100 degrees C. So there is an oxide layer in the silicon carbide particles. The oxide layer is good for the wettability between this silicon carbide and aluminum. Then we can protect the detrimental phase that is aluminum carbide. That is.
Okay. Professor Tanaka, so you present that the silicon single wall carbon nanotube and something like that. Is there any other alternative material other than that single wall carbon nanotube?
Yeah. So we have some requirement for such a random network. So, for example, non-linearity, we need to make many electrode input output, and each output should have a non-linear property, and the phase shift, and higher harmonics. So that's three most important requirement for the reservoir task. And then we move to the benchmark task for the air systems.
Okay, thank you. Prof. Anna.
Yes.
Is it possible for the aluminum metal matrix composite to make a nozzle to get lightweight requirement, nozzle for rocket or something like that?
Yes, it's possible. Yeah, thank you, Anana. Yes, it's possible, but we need the industry. So here in Indonesia, more of industry, they don't use the metallic composite here. They only use the monolithic materials such as the aluminum or even steel. For the rocket body tube, we need the lighter materials that we can obtain by metal composite. But of course, this metal composite, because there is a ceramic inside, so the ceramic can withstand at high temperature. So it's better for our small rocket here. Lapan has a small rocket that is RX-122. So for the small rocket, we need lighter materials in order to improve their performance. But unfortunately, we don't have the industry to produce the metal composite tube here. But we can make this metal composite tube by our process. But unfortunately, we don't have such equipment to produce a large tube. We only can produce the prototype one. But
Okay.
of course, if our industry wants to develop this material for our rocket tube, so I think it's possible, but all depend on the industry.
Okay, yeah. Sorry, because Professor Huang is already have a meeting, so there is a question about the silver wire. So this is the question: is there any possibility of using the other noble metals? So I have the voice note of his.
Thank you for your comment, and yeah, this is a really nice question. So so we can use the other noble metal nanowires too, but the silver nanowire is cheaper than other noble metal nanowires such as the gold or platinum, and also the synthesizing method of silver nanowire is easier than the other noble metal nanowires too. So so that's why the silver nanowire is one of the most promising noble metal nanowires. And we can also think about some cheaper nanowires such as the copper, but it's really difficult to suppress the oxidation of these copper nanowires. So silver nanowire, currently up to now, this silver nanowire is considered as the best option for this flexible electronics. But if you can develop some cheaper nanowires such as copper nanowire with the excellent oxidation resistance, then we can, I'm sure I will definitely use that kind of copper nanowires. Thank you.
Okay, maybe if that question answer is a help. So we already in the end of our session. So I would like to ask Professor Tanaka and Professor Anna to give their last statement. Can you say something? Prof. Tanaka
So
first?
Who first? I'm first? Okay.
Yeah, okay. Prof. Anna, please.
Okay, thank you, Pak Nono. I'm great pleasure to join with this conference. It's quite prestigious conference here this morning. Even this conference is virtual conference, but a lot of my colleagues who join with this conference. I hope you are success to do this conference even for today and next time perhaps. So I'm very sorry that I cannot send my student to this conference because we have the same activity during this week. We finished all of the conference last Tuesday, so most of my students cannot join with you. Perhaps because usually every year we send the student to join with this conference, we can get a lot of information, we can get a lot of knowledge here, a lot of keynote speakers who join with this conference. Therefore, I said this prestigious conference that we can improve our knowledge, we can share our knowledge. So thank you for the committee who has invited me to join with this conference. Thank you, Pak Nono.
Okay, you next, Professor Tanaka.
Yeah, okay.
Can you say
Thank you.
something?
Yeah, thank you for inviting me in such a great conference, and I'm very impressed the plenary talk than me, and actually I had as you know I had several Indonesian students in my group, and also welcome the student in PhD course in my group. So anyone, I think Indonesian student is very smart and good for research in my group. So I welcome such a student. Thank you very much.
Okay, thank you very much, and thank you for Prof. Anna and Prof. Tanaka for your time and for great presentation, for sharing your knowledge also. So I invite you all the participants to open your webcam. So we will have a photo session to finish our presentation now. Maybe can we help from the host to take a picture and give your biggest smile. So for the moment, please take off your mask.
Yes.
So we can see your face.
Are you ready? Okay, wait.
Yeah, please.
Yes, everyone is now opening their video. Okay, I will take the first slide. 1, 2, 3. Okay, just a moment. Okay, now I'm going to the next slide, second slide. There are 2 slides here for the videos. Just a moment. I'm gonna take this one. 3, 2, 1. Okay, taken. That's all. Thank you.
Okay, thank you. Thank you all for your attention and for your time. Now we are finished for this plenary session. Thank you again for Prof. Anna and Prof. Tanaka. Maybe we can share next time again. So this time finish my job as a moderator for this plenary session. Thank you again for your attention. Maybe I will give this to the MC.
Okay, thank you very much. Terima kasih.
Yeah, thank you very much. Terima kasih.
Yeah, keep in touch. See you next
Okay,
time. Bye.
Terima kasih, Bu
Bye.
Ana.
Thank you, Pak Nono. See you
See you
sometimes.
time.
So I will
Mungkin-
leave.
Yeah, thank you very much, Prof. Anna.
Thank you, Pak
I'm
Nono.
also leaving. Thank you.
Yeah, thank you, Prof.
Okay, see you,
Tanaka.
Professor Hirofumi
Yeah,
Tanaka. Thank you. See you sometimes.
Stay in touch,
yes.
stay healthy, and
Thank you. So keep your hold.
where's the?
Maybe we can do directly now. Just for all
Yeah.
participants of the parallel session, please immediately join your own room A or room
Thank you very
B.
much for your join this plenary session.
So for the presenters who are still in the main lobby, please read the chat message to everyone. Then you can find my message. We already opened 2 rooms, room A and room B. But if you could not enter your own room, please tell me by direct message, by private message. But I think if you already update your Zoom into the latest version, then you could easily find the breakout rooms by yourself. And then you can join freely, whether you want to join room A or room B. Then make sure you should be ready by 5 or 10, yeah, maybe 10 minutes is better before your own presentation. Okay, for Bu Titik, I already assigned you to room B.
Beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat. Meliputi
Okay, good morning, ladies and gentlemen. Today we will hear presentation from three presenters, Dr. Andri Hardiansah, Dr. Anawati, and Indah Primadona. We have 5-10 minutes for each presenter, 10-minute presentation and 5-minute question and answer. For Dr. Andri Hardiansah, please, the time is yours.
Okay, I will share my file first. Have you seen my presentation?
Okay, we can see. Yeah, please, Dr. Andri.
Okay. I'm sorry. Okay. Okay, thank you for the time, the moderators. Okay, good morning, everyone. Today, I would like to present my current research in our lab about the characterization of microwave irradiation, assisted transformation of reduced graphene oxide for photocatalytic material-based water treatment application. My name is Andri Hardiansah from Research Group of Low Dimensional Functional Material, Research Center for Physics, Indonesian Institute of Sciences. And here is the outline for my presentation today. The first, I would like to give some information about the graphene oxide and reduced graphene oxide, and then continue with materials and methods. Result and discussion. In this section, I would like to decide into two parts. The first one about the characterization of reduced graphene oxide through microwave heating. And the second part about the fabrication and evaluation of reduced graphene oxide titanium dioxide nanocomposite herein for photocatalytic application. And the last, I would like to conclude and then give some future prospect. Okay, as we know, graphene-based material actually another family of the carbon-based material which could be derived from the graphite. It's very interesting materials nowadays. A lot of researchers have been done with this research actually. And actually the graphite can be oxidized into graphene oxide with several methods. And then so many established methods have been done with this. And graphene oxide actually carbon-based materials, which is rich of oxygen functional group like epoxide, hydroxyl, carboxyl, and carbonyl attached on the surface of the graphene oxide. And then because of this functional group, graphene oxide has a hydrophilic properties. And then graphene oxide could be reduced into the reduced graphene oxide, which is some of oxygen functional group have been removed on the surface of the graphene oxide. In here, we could also recover the electronic conductivity of the reduced graphene oxide. So each of this type of carbon-based material has its own properties. So we could choose the best properties for what application. And then actually a lot of methods have been done to prepare the graphene oxide. And in our research, we choose the liquid phase exfoliations since it's feasible to be conducted in Indonesia, which is a very low cost, but we still can adjust some properties for some application. And in respect with the reduced graphene oxide, actually we could transform the graphene oxide into reduced graphene oxide with several methods actually, like reductant reduction, electrochemical reduction, microbiological reduction, and irradiation reduction. In each process has its own disadvantages and also has its own advantages. Like if we use the reductant reduction, which is using the chemicals for as a reductant, it's somehow it's toxic as it's not really applicable for some application. So in our research, we use microwave irradiation in order to transform the graphene oxide into the reduced graphene oxide easily. And actually, why microwave? Microwave because heat is distributed uniformly, so we can generate the rapid heating, and then it's non-contacting method, and actually it's economically cheap and ultra fast and efficient method to develop the reduced graphene oxide, and somehow it can be a very eco-friendly. And actually, so many researchers have been done with this, as you can see in my screen. A lot of parameters have been done also, and they use for so many applications. And here is some characteristic of the reduced graphene oxide, but actually the solubility is insoluble in water for some concentration. And the electrical conductivity actually quite high rather than graphene oxide. And then the beta surface area, which for the surface area of the reduced graphene oxide, it's about 400 until 500 meters square per gram. And based on the literature, the elemental analysis dominated by carbon, but we could note that the oxygen still attached on the surface of the reduced graphene oxide, actually based on, depends on what kind of the processing, but we can see that there is still some oxygen content on the reduced graphene oxide that might be affect to the properties of the reduced graphene oxide. And then the application of the reduced graphene oxide, actually a lot of application we can choose. In my research, actually, I would like to try some maybe famous application related to the composite for photocatalysts. However, we can still use the reduced graphene oxide for some application in respect with advanced materials like battery, biomedicals, supercapacitor, unpredictable graphene electronics. Maybe in the future we can do this kind of application. And then in respect with photocatalysts, actually, we will talk about the semiconductor nanomaterials, and so many researchers have been done with this also. And then we can choose a lot of nanomaterials that we can composite with the reduced graphene oxide. However, in let's say this preliminary research, I would like to try the titanium dioxide because it's efficient photoactivity, excellent chemical and photochemical stability, and also relatively low cost, and then safety to human and environment. However, actually some maybe some drawbacks in the titanium dioxide because it's only active in ultraviolet region, which is only 4% of the incoming energy. Meanwhile, we know that the light comprise about 40% of visible light energy. Okay, here is the methodology we try to use in our lab. Actually, there are two parts. The first one is the synthesis of graphene oxide and transformation of graphene oxide into the reduced graphene oxide. And here we use the Hammers method. It's like a very well-known method. It's also a very old method used for the preparation of graphene oxide. So many researchers using this kind of method in order to prepare the graphene oxide. Basically, we use the strong acid in order to oxidize the graphite, and then using also some chemicals in order to react the reaction. And then we actually we have developed a very stable graphene oxide, a very nice graphene oxide solution, a dispersion. And then after that, after we prepare the dispersion of graphene oxide, so we transform the graphene oxide into the reduced graphene oxide by using the microwave irradiation. Herein we use the commercial microwave in order to transform the graphene oxide into the reduced graphene oxide. In respect with the titanium dioxide, we also put the titanium dioxide in the reaction, mixing by ultrasonication with the graphene oxide, and then we microwave immediately. And the second part, after we prepare the graphene oxide and reduce graphene oxide, we do the catalytic, we did the photocatalyst experiment by using rhodamine 60 as a model for pollutant. And also we try to irradiate it, them by UV light, and then just measure immediately by using UV spectroscopy to see the properties. And then here's the result and discussion. The first about the characterization of the graphene oxide and their family, and then the second part about the fabrication for photocatalyst experiment. And then here is the some structures developed and evaluated by some characterization, microscope characterization, by using TM, VSEM, and then we could see that the graphene oxide is a very thin layer. It's very nice picture for the layers of the graphene oxide. And then by the visual observation, actually we could evaluate the transformation of graphene oxide into the reduced graphene oxide. Why? Because the graphene oxide actually originally like a brownish color solution. However, the reduced graphene oxide changed into the black color solution. and then black precipitate a little bit. And then for the reduced graphene oxide, actually not so fancy characteristic or fancy structures, but we can see the wrinkle structures of the reduced graphene oxide. And then we also try to use the UV spectroscopy in order to evaluate the transformation. And we see that the transformation already occur in the reduced graphene oxide, yeah, due to the transition into the 270 nanometers. Meanwhile, in graphene oxide, originally they have a very specific UV characteristic in 230 for the transition of pi axon for aromatic CC. And in all of samples, they generate the transformation evaluated by the UV spectroscopy. And then another characterization would be the Raman spectroscopy. As we know, the Raman spectroscopy is a very powerful method in order to check the characteristic of the carbon-based materials. Here in some selected samples that we observe by using the Raman spectroscopy, and we know that the Raman spectroscopy will confirm the D-band and G-band as the most important characteristic for carbon-based materials. Here in the RGO that we produce still consists of the D-band, means there is some defect in the structures of the reduced graphene oxide, probably due to the microwave irradiation. And then some FTIR spectroscopy in order to see the deoxygenation during the microwave irradiation, that we believe due to the heat, some hydroxyl molecules removed from the reduced graphene oxide samples. And then that's the first part that we probably successful in order to transform the graphene oxide into the reduced graphene oxide through the microscopic evaluation and spectroscopic evaluation. And actually, the photocatalyst application, we just wonder how it can be done for using reduced graphene oxide.
You have 2 minutes remaining.
Okay, thank you. And then the same, we use the Raman spectroscopy in order to check the structures of the morphology and structure of the reduced graphene oxide. We see clearly the difference, the improvement of the composite of reduced graphene oxide and titanium dioxide. And then by checking the photocatalytic experiment, we see that by using reduced graphene oxide titanium dioxide, we see that the rhodamin 6G already try to degrade by the time of the UV irradiation, means that some rhodamin 6G have already degraded and decomposed by using the checking of the UV spectroscopy. And then here is some figures, image that we use the, sorry for the typo, we use the rhodamin 6G 2 hours, 100 milliliters, and we see that there is a color change, means the degradation of the rhodamin 6G. And then here's some role of RGO in photocatalyst. Actually, there's 3 crucial factors. There is a charge transportation, charge carrier, and light absorption. And that we believe that reduced graphene oxide plays an important role in the photocatalyst due to the electron storage. So the electron storage could react with the oxygen and then produce the oxygen radical that attack the pollutant. And then for the conclusion, we believe that the reduced graphene oxide is successfully prepared to microwave irradiation, and then we have already decomposed and degrade the rhodamin 6G by using the titanium dioxide reduced graphene oxide nanocomposite. Okay, that's all for my presentation, and thank you for your attention.
Thank you for your presentation. If you have any question, you can turn on your microphone and you can ask directly to Dr. Andri. Okay, is there any question, please? Okay, Dr. Andri.
Yes.
You use microwave for synthesize graphene oxide. So can you explain the relation between defect density and the power of microwave in your experiment? Okay.
Yes. Okay. Thank you for the question, Dr. Yudi. Yes, actually, in respect with the defect density, we try to use the Raman spectroscopy. However, the result not shown here. And actually, by using increasing the microwave times, the defect is increasing. We check the ratio of the density band over the G band is increasing during with the increasing of the microwave powers. Mean the defect is the defect still exists on the RGO, on our RGO. And actually also it's also still debatable in the RGO research, because yeah, I see some research in reduced graphene oxide in respect with the temperature, actually, because yeah, higher microwave powers mean the higher temperatures. They also confirm that increasing the temperature will generate more defect in the structures of the reduced graphene oxide. And we have checked it by using the first we checked by using the reduced graphene by using the Raman spectroscopy in order to check the defect of the reduced graphene oxide. So by using the ID over the IG ratio by using Raman spectroscopy, increasing the power of the microwave will increase the defect on the reduced graphene oxide.
Okay, thank you,
yes.
Dr. Andri. Nice presentation, nice time picture, and we will continue to next presentation.
Okay, thank you so much.
From Dr. Anamati. From now we will hear the presentation from Dr. Anawati. For the we will hear the video from Dr. Anawati, please.
Morning, ladies and gentlemen. It is an honor to be part of the 4th International Symposium on Metallurgy and Materials. I always join this symposium every year. My name is Anawati. Today I represent one of my undergraduate students on the works entitled Postmortem Study of Fracture Surface of Chrome-12 Blade Used in a Steam Turbine. We are from Physics Department, University of Indonesia, and this work is in collaboration with Indonesia Corrosion Association. Carbon steel are widely used in the power plant industry because of its suitable mechanical properties such as strength and modulus. The standard material for low-pressure turbine blade is carbon steel chrome-12. This material contains iron about 85 weight% and chrome-12 weight%. The chrome content provides passive oxide layer on the surface to protect the material from corrosion. Turbine is one of the essential parts of the power plant that converted the high-energy gas to mechanical work. The exposure to high temperature often causes fatigue failure. Statistical data show that most of the power plant accidents caused by a turbine fracture. One of the turbines in the Suralaya power plant experienced fracture. The turbine has been used for 33 years, which already fulfilled the design of lifetime. There is a need to recycle the material for other purpose. Therefore, we characterize the microstructure and mechanical properties of the fracture surface. The material was exposed to carbon dioxide, carbon monoxide, and hydrogen sulfide gas environment as a result of coal combustion. Characterization was done first by observing the microstructure using optical microscope and scanning electron microscope. To reveal the microstructure, the specimen was etched using Kalling reagent containing copper chloride, chloric acid, and ethanol. The chemical composition was checked to observe the corrosion product if existed using XRF or X-ray fluorescence and EDS or energy dispersive spectroscopy, whereas the phase composition was analyzed by X-ray diffraction on both surface and rear surface. The mechanical properties were investigated by tensile test and hardness test according to the ASTM E10. The hardness test used Brinell method using tungsten carbide indented with load 1200 kilograms. Here is the chemical composition detected by X-ray fluorescence. The main elements detected in the fractured material are iron and chrome with concentration 73% for iron and 16% for chrome. The chrome content was 3% higher than the reference for S-manufactured chrome 12. Chrome was possibly enriched on the surface of grain boundary as a result of high temperature exposure during operation. And remember, the environment, which was rich in carbon dioxide, carbon monoxide, and hydrogen sulfide gases, may lead to the enrichment of chrome carbide and chrome oxide. And also, it is worth to note that copper content is higher in this material, about 2.9 weight%. To confirm the composition of the fracture section, we analyzed the specimen with EDS. Here is the EDS result on a rectangular area on the surface. The specimen contains 66.7 weight% iron and 14.4 weight% chrome. Although chrome concentration is lower than that obtained from the XRF analysis, it is still higher than the reference. Nickel content is rather high as well, 4.5%, whereas in the reference, it is supposed to be less than 0.6 weight%. And also, it is worth to note that the carbon content was 2.2 weight%. Confirming the XRF results, the specimen also contained copper as high as 3.8 weight%. By XRD detected only 3 distinct peaks corresponding to the iron alpha phase with BCC or body center cubic structure on both the surface and cross-sectional surface. The enriched chrome compound detected by XRF in EDS were not detected by XRD. They were possibly existed in amorphous state, or the crystal size was too small to be detected by the XRD. These are the optical microscope image of the fracture surface showing fracture lines and beach marks. The lines and beach marks are commonly observed on a fracture surface of iron-based metal as a result of fatigue. Fracture usually initiated from the beach mark. The beach mark indicated that fatigue is the main cause of failure of the blade. The intergranular crack indicated embrittlement, which possibly due to precipitation of the hard phase of carbide, possibly chrome carbide, along the grain boundary. Precipitation of carbide occurs at a temperature around 500 to 600 centigrade, and this is the higher magnification image showing the martensite structure that become clearer. This is the optical microscope image at a higher magnification and the 3D view of the surface. The plan view image shows the martensite structure with small and elongated grain, and the surface was relatively flat with homogeneous grain structure. This is the same image showing many voids existed on the surface. The voids are indicated by the white arrow in the image. Voids were likely formed due to diffusion of hydrogen gas into the material. Hydrogen atom induced plastic deformation in the material. The local hardness increased and the material ductility decreased. Under the load, hydrogen embrittlement may occur, which causes transgranular crack. Confirming the SEM result, the tensile strength of the material was very low at 95 megapascal, which was 5 times lower than the reference. The yield strength was also low, about 3 times than the reference, while the strain remained in tolerable number. However, the material was harder than before than the reference, so it is 324 compared to 240 of the reference. Is the existence of voids and beach mark on the fracture section indicate that the blade material experienced fatigue failure. The voids were formed as a result of hydrogen diffusion, which embrittled the material. Hydrogen atom increased the material hardness and lowered the tensile and yield strength. For further use of the material for other applications, rejuvenation of material is necessary, possibly by high temperature treatment or recasting. Thank you for your attention. Okay. Good morning, ladies and gentlemen. It is an honor.
Okay. If you have any question, please you can type or ask directly to Dr. Anawati. Is there any question? Okay. Dr. Anawati, can you hear me?
Yes.
Yes. There is. I have one question for you. Can you explain more detail crack initiation by hydrogen embrittlement? How could this phenomenon happen, and how to detect the crack initiation from hydrogen embrittlement?
Yeah,
Thank you.
thank you. Thank you very much for the question, Dr. Yudi. So actually this material is already experienced failure, and we try to find out what is the cause of the failure. And we found that there are many voids in the inside the material already, and then we after we found that void, then we assume that because of the environment is enriched with hydrogen sulfide gas, so there are a high chance that the hydrogen can diffuse into the material, especially the operation temperature is really high, and it is possible that hydrogen diffuse and then it embrittle, cause deformation, plastic deformation inside the material, and the evidence is we can see the voids, and the local embrittlement occur at the deformed material. So at the deformed site, embrittlement by hydrogen is occurred. So well, actually this material we cannot use it any longer for blade, but we want to sort of recycle the material for other purpose. So what we can suggest is to recasting the material, or maybe we can do high temperature heat treatment to refresh all the mechanical properties. So maybe that's what we can explain.
Okay. One more question, Dr. Anawati. What is the influence in the presence of 4% in nickel in your sample? This is from forum. Thank you.
Oh yeah, nickel, actually nickel is already there for weight percent. We couldn't find the influence for the failure that occurred. I don't think it's because of nickel, because we found the voids, the evidence is voids. So we accuse that hydrogen is the main cause of the failure. So for until now, we couldn't explain what is the role of nickel and copper, because we also found copper rather high. It's supposed to be less than 0.6, but we found 3.8 weight percent. So we don't know. Probably it's from the manufacturer. They already added copper and nickel in the material for some reason that we don't know, because we received the material already in the condition of fracture. So and we only know the condition of operation. So the conclusion is only based on evidence, And we can conclude it's the hydrogen that play a significant role in the fracture, not the composition of the material. I hope that explained the question.
Okay, nice explanation, Dr. Anawati.
Thank you.
Thank you for your nice explanation and your nice explanation about failure analysis. Now we can continue to the next presenter, Indah Ramadona. The title is Green Synthesis of Silver Carbon Nanocomposite for Enhancing Antimicrobial Activity. Now we learn the video from Indah Ramadona.
Hello everyone, my name is Indah Ramadona. I'm from the Institute of Green Technology Indonesia Institute of Science. Here in the fourth international seminar on technology and materials 2020, I would like to present about our work entitled Green Synthesis of Silver Conjugated Carbon Nanocomposite for Enhancing the Antimicrobial Activity. If we talk about the nanotechnology is science, engineering, and technology conducted at the nanoscale, which is about 1 up to 100 nanometers. Nanotechnology is an interdisciplinary science. Material nanomaterials possess unique physical, optical, electronic, and biological properties compared with their counterparts. And these unique properties at the nanoscale have led to the use of nanomaterials in fields where conventional materials have limitations. Up to now, nanotechnology has been used in many fields, such as medical, environment, sensor, electronics, energy, catalyst, and cosmetics. As you can see here in this slide, that engineered nanomaterial such as silver, gold, titanium, or zinc oxide nanoparticles can be found in many commercial products, such as in cosmetic products, textile, electronics, medical equipment, etc. In order to produce the engineered nanomaterial for various applications, as I mentioned in the previous slide, what you need to consider is the chemical composition, size and morphology, and also the dispersity. In general, there are two main approaches. First is the top-down approach, where the building blocks are removed from the structure to form the nanostructure, while if the building blocks are added onto the substrate to form the nanostructure, can be called as the bottom-up approach. Processes that include a top-down approach are mechanical or bonding, chemical etching, thermal or laser ablation, sputtering, and all of these processes relatively need high energy. In another hand, bottom-up approach such as chemical reduction, UV-initiated photoreduction, photo-induced reduction, electrochemical, and microelectrolysis mostly need chemical substances as a reductor, which is usually toxic. Nowadays, many people try to develop a green method, which involve bacteria, fungus, or plant extracts. Green chemistry, which was established about 2 decades ago, has attracted much attention. Briefly, green chemistry is the utilization of a set of principles to reduce or eliminate the use of generation of hazardous substances in the design, manufacture, and application of chemical products. Green chemistry is a multidisciplinary field and covers areas such as synthesis, solvents, catalysis, raw materials, product, and efficient processes. In this work, we try to develop a green method for synthesizing the nanoparticles, particularly silver nanoparticles. In this process, we concern on the using of green solvents, green and renewable raw materials, and efficient process. In the last decade, carbon dioxide has been explored and using as a reductor and stabilizer in the synthesizing metal nanoparticles, particularly gold and silver nanoparticles. These are several papers that have been published related to that. Several sources of carbon dioxide was used, whether sources from pure compounds or natural products.
Indonesia is one of the agricultural countries in the world. One of the largest agricultural commodities produced in Indonesia is the rice. Therefore, in consequence, the rice straw waste is also very abundant. In this study, we use the rice straw as a source of carbon dioxide. In order to obtain aqueous carbon dioxide solution, we tested two different kinds of green methods, hydrothermal and microwave. And this is the image of the carbon dioxide obtained by the left side is obtained by the microwave and the right side is obtained by the hydrothermal. In order to synthesize the silver nanoparticle, we use silver nitrate as a precursor and mix with the carbon dioxide and then apply the sound wave or using a stir to produce a gray solution. These are the usable spectra and photoluminescent spectra of carbon dioxide obtained by hydrothermal transit non-fluorescent method. As you can see here in the usages of this spectra, both carbon dioxide solution show the absorption at a wavelength around 270 nanometers, and this is characteristic for electron transition type to type chart. It means that the core of the carbon dioxide contains of sp2 and sp3 differentiation. Using the hydrothermal method, there is an addition of the peak at around 325 nanometers. And this is a characteristic peak for electron transition and to type chart. So this indicates that in the surface of the carbon dioxide contains of the functional group hydroxyl and carboxyl, and it cannot be observed in the carbon dioxide solution by using the microwave method. If you see the photoluminescent spectra, carbon dioxide generated by the hydrothermal method gave a higher emission continuous compared with the microwave method. This image also shows clearly that the carbon dioxide obtained by the hydrothermal is brighter than the carbon dioxide achieved by the microwave method under the UV light. In order to analyze the chemical element present in the carbon dioxide solution, EDS experiment was conducted. According to these two spectra, carbon dioxide solution generated by the hydrothermal method is more pure compared with the microwave. So, according to the all characterization results, the hydrothermal method is more suitable compared with the microwave in synthesizing the carbon dioxide from the rice straw. So, in the next step, we optimize the hydrothermal method by varying the time of heating, 2 hours, 3 hours, and 4 hours. According to the usages and photoluminescent spectra, there is an enhancement of quantum yield.
by increasing the time of heating. For the next characterization, we use the carbon solution of time from 4 hours hydrothermal process. Infrared characterization results is in agreement with the ubiquitous absorption spectra. So as you can see here that carbon with the active hybridization is active in the carbon dot, and hydroxyl carbonyl is also present in the surface layer of the carbon dot. Chemical element of carbon dot is quite pure. So only carbon and oxygen was observed. And according to the CEM image, the size of carbon dot is around 10 nanometers. These are the characterization results of silver carbon dot nanocomposite product. The formation of silver nanoparticles can obviously be seen in the ubiquitous spectra by appearing the new peak at around 450 nanometers. The EBS spectra also show that the silver element is also active. Based on the CEM image, a silver nanoparticle was coated by the carbon dot, and the size of the composite was distributed widely below 100 nanometers. In order to evaluate the effect of the carbon dot coating on silver nanoparticle on the antimicrobial activity, we tested and compared the naked silver nanoparticle with the silver coated by the carbon dot. Two different kinds of bacteria were used in this experiment, Staphylococcus aureus and E. coli. By measuring the zone of inhibition for both different kinds of bacteria, there is likely enhancement if the silver nanoparticle was coated by the carbon dot. So, in summary, we can conclude that the hydrothermal process resulted in better carbon dot properties compared with microwave method. And at concentration of 5,000 ppm, carbon dot coated silver nanoparticle synthesized by carbon dot obtained from rice straw waste exhibit slightly better antibacterial activity compared with naked silver nanoparticle. Finally, I would like to thank to the audience for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Hello, good morning, Dr. Indah. Can you?
Good morning.
Good morning.
Thank you.
Please, if you for audience, please, if you have any question, you can directly ask to Dr. Indah. Is there any question from the forum? Okay. Okay, Dr. Indah, I have one question. In slide number 8, you mentioned that you have you compare photoluminescence from hydrothermal and microwave. And can you explain why the photoluminescence intensity from microwave and hydrothermal difference? And please, Dr. Indah.
Okay, thank you very much for the question, Mr. Yudi. Okay, yeah, actually we try two different kind of a green method for the synthesis of carbon dot. They are microwave method, our microwave approach, and also the hydrothermal approach. And yeah, we observe actually by using the hydrothermal with the same time of the reaction, that I think, as I remember, that was 2 hours, and process is more efficient than the microwave, probably, because there is the pressure of that, right?
Okay, thank you, Dr. Indah. Nice explanation and nice research, because in Indonesia, photoluminescent research with nanocarbon, especially carbon dot, is
we also collaborate with Dr. Ismaini from the Physics Research Center.
11:30. We will meet again at 1 o'clock. Thank you for your attention, and hopefully you can enjoy this presentation, this session, and see you at 1 o'clock. Thank you very much.
Berawal dari cita dan asa untuk membangun negeri, memberikan segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif, dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian, berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung Iptek di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka konservasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia, infrastruktur riset strategis, dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi, material maju, energi, teknologi, informasi dan komunikasi, pertahanan dan keamanan, dinamika sosial, kemanusiaan, mewujudkan diri sebagai lembaga ilmu pengetahuan Indonesia yang andal, profesional, inovatif dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah Kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung Iptek di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka konservasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 koleksi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia, infrastruktur riset strategis, dan beberapa pusat berskala internasional yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi. Berawal dari cita dan asa untuk membangun negeri, memberikan segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif, dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian, berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung Iptek di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka konservasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia, infrastruktur riset strategis, dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi, material maju, energi, teknologi, informasi dan komunikasi, pertahanan dan keamanan, dinamika sosial, kemanusiaan dan kebudayaan, kebencanaan, inovasi teknologi dan pendayagunaan iptek, pelayanan, pengujian dan pembinaan ilmiah, serta peningkatan kualitas SDM iptek. Kerjasama keilmuan LIPI dalam negeri meliputi kerjasama penelitian, lisensi teknologi, pengembangan, aplikasi dan komersialisasi hasil penelitian, kerjasama non-penelitian, dan konsultasi kepakaran LIPI. Sedangkan kerjasama luar negeri, LIPI melakukan joint research, workshop, pertukaran peneliti dan beasiswa mancanegara, selain aktif menjadi anggota dan focal point di berbagai organisasi internasional. Melalui kolaborasi bersinergi, menghasilkan riset yang berkualitas, LIPI terus memberikan manfaat nyata, kontribusi berarti, dan turut mewujudkan cita dan asa membangun negeri kita tercinta, Indonesia. Berawal dari cita dan asa untuk membangun negeri, memberikan segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM pendukung IPTEK di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka konservasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia, infrastruktur riset strategis, dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi, material maju, energi, teknologi, informasi dan komunikasi, pertahanan dan keamanan, dinamika sosial, kemanusiaan, dan kebudayaan, kebencanaan, inovasi teknologi dan pendayagunaan iptek, pelayanan, pengujian, dan pembinaan ilmiah, serta peningkatan kualitas SDM iptek. Kerjasama keilmuan LIPI dalam negeri meliputi kerjasama penelitian, lisensi teknologi, pengembangan, aplikasi dan komersialisasi hasil penelitian, kerjasama non-penelitian, dan konsultasi kepakaran LIPI. Sedangkan kerjasama luar negeri, LIPI melakukan joint research, workshop, pertukaran peneliti, dan beasiswa mancanegara, selain aktif menjadi anggota dan focal point di berbagai organisasi internasional. Melalui kolaborasi bersinergi, menghasilkan riset yang berkualitas, LIPI terus memberikan manfaat nyata, kontribusi berarti, dan turut mewujudkan cita dan asa membangun negeri kita tercinta, Indonesia.
Okay, good morning everyone. So we will begin the second session of day 2 of Ismm 2020. So there is from 1 o'clock until 12 o'clock we have 6 presenters. So in this session we will begin the presentation from Dr. Anawati. For Dr. Anawati, please the presentation. Please video the presentation.
It is honor to be part of the 4th International. Assalamualaikum warahmatullahi wabarakatuh. Welcome everybody. It is honor to be part of the 4th International Symposium on Methodology and Materials. My name is Ade Rahman Fauzi. I come from the Physics Department University of Indonesia. Today, I present the result of my research entitled Characterization of Fracture Section of Modified HP40 Pipe in Ammonia Primary Reformer. This research in collaboration with Indonesia Corrosion Association. Natural gas contains several chemical compounds, namely methane, hydrocarbon, ethane, propane, and butane. In addition, natural gas has several undesirable impurities such as nitrogen, carbon dioxide, water, and hydrogen sulfide. Raw materials of natural gas resource can be either ammonia, methanol, or dimethyl ether. Ammonia is the raw material for the production of volatile urea with an average boiling point of -33 degrees Celsius at atmospheric pressure. Liquid ammonia is the preferential form for secure storage. The liquid state is obtained by applying high pressure and low temperature processing to condense the gas into a liquid. Reformers are used to extract natural gas such as methane into hydrogen, carbon monoxide, methanol, and ammonia. Some parameters that shall be controlled during the process are temperature, pressure, and ratio between natural gas and water vapor. Ammonia production uses a reformer unit inside the reformer, an endothermic reaction process, as the natural gas reacts with water vapor or steam. The inlet gas has a temperature of 406 degrees Celsius and pressure of 40 2 kg per centimeter square with a steam and carbon ratio of 2.5 until 3. The mixture of gas and steam is heated to a temperature of 610 degrees Celsius and then distributed into 12 subheaders with each subheader comprised 42 pipes. The pipe was made of a modified HP pipe containing a NEO catalyst, arranged vertical typical endothermic reaction that occurred inside the reformer pipe are follows. The following are the pipe specifications used for the reformer in this study. The type of pipe used is HP modified 23 chromium, 35 nickel titanium or HP mod 40. The design lifetime is 100,000 hours. It has been used for 87,600 hours in the operating of the reformer. The outer diameter of this pipe is 123 mm and inner diameter of the pipe is 114 mm. The thickness of this pipe is 9 mm. The design temperature is 887 degrees Celsius. The design pressure is 38 bar. Whereas in industrial operation, the temperature is 900 degrees Celsius, with the operating pressure is 33 bar. In this part of the research, the samples taken are the back side of the pipe that is damaged or broken. The purpose of this research is to characterize the cause of failure of the modified HP40 pipe and to predict the remaining life on the modified HP40 pipe. The method used in this study was mechanical preparation and characterization. In mechanical preparation, the first thing to do is cutting. When cut, the sample were cut into 1 cm, cross 1 cm, cross 1 cm size for optical microscope characterization, X-ray diffraction, and scanning electron microscope and energy dispersive X-ray spectroscopy. As for the characterization of the crypt test, the sample were cut with the ISTM E8 standard. After cutting, grinding, and the polishing, there are 4 things to do for characterization. The first is an optical microscope observation. Then aim to see the microstructure of the pipe sample. The second is XRD, which aim to see what phase are formed in the sample pipe. The third is SEM-ADS, which aim to determine the morphology, topography, and element contained in the sample. And the fourth or last characterization is the crypt test. This crypt test aims to find the remaining life of the sample using the Larson-Miller parameters method. Results and discussion. The result obtained from the optical microscope, the microstructure in the figure showing the deposition of carbide, both primary and secondary. Primary carbide are located along grain boundaries, resulting in thicker and duller boundaries. Secondary carbide are observed in the grain bodies and discrete particles. The carbide phase is known to increase the mechanical hardness of iron-based metals. Multiple CVTs are also detected randomly in the alloy, As indicated by the arrow in figure, the cavities on display were in the range of 20 until 50 micrometer. Trapping hydrogen gas either during manufacture or during exposure to the environment creates vacancies in the bulk material. This cavity, if it occurs, is very large and can cause the pipe to break or the damage. The result of XRD characterization is that the detected phase in the austenitic phase reformer exposure does not cause a phase in the alloy. The result of semi-ADS characterization showed the fracture morphology seen from the cross-section showing the outer and inner surface of the pipe and ADS analysis of the outer surface. Figure A, we can observe that the outer surface shows a curved fracture with a surface roughness of 200 until 450 micrometer. In contrast, for figure C, we can observe that the inner surface is relatively smooth, with a surface roughness of 15 until 25 micrometer, and for figure B shows the plan view morphology of the outer surface and the corresponding EDS analysis figure D. The outer surface is very rough and crunchy and is decorated with holes. EDS analysis shows high carbon and oxygen concentration on the surface with a concentration of 29% and 27%, respectively. The outer surface is covered by the deposit layer containing carbon and oxygen. Although there is a deposit layer and the high carbon content can be attributed to the carbide base. Other elements including iron, chromium, nickel, aluminum, silicon, and carbide are derived from the underlying alloys.
Thank you, Mr. Moderator. If could you play the video for Mr. Jan Setiawan?
Assalamualaikum warahmatullahi wabarakatuh. The Honorable Moderator, speakers, and participants, it gives me a great pleasure to be presenting our paper with the title Structural Analysis on In Situ High Temperature XRD of Corundum, written by Mr. Jan Setiawan, Mr. Slamet Pribadi, Mr. Husna Alhassa, and myself, Ganisa Kurniati Suryaman from Center for Nuclear Fuel Technology, Batam. This is the outline of my presentation today. First is the introduction. Second one is experimental method. Third one, result and discussion. And the last one is conclusion. Now we are coming to the first part of my presentation, which is introduction. Nowadays, high temperature materials are widely used for industrial application. Therefore, the necessity for materials analysis at high temperature become an inevitable need. An XRD analysis is one of the methods that can be used to characterize materials at high temperature. And as we know that corundum is one of the refractory materials that commonly used in industry, and it is a stable type of aluminum oxide. Therefore, this material is suitable to use in order to characterization in situ high temperature XRD of material. So the investigation on structural changes of the corundum during heating using in situ high temperature XRD apparatus and its analysis were conducted to show the corundum behavior at high temperature. These are the materials and apparatus that we use for characterization. For the XRD analysis, we use the XRD machine from Analytical, and for the powder characterization, we use the particle size analyzer from Microtech, and this is the corundum powder. Before we do the in situ high temperature analysis of corundum, first the corundum powder that we use, we disperse it in ethanol, and then the dispersed powder were placed on the surface of the platinum plate inside the sample stage apparatus. And the full profile was observed at 2 theta angle from 20 to 75 degrees. And high temperature was observed at 100, 200, and 300 degrees centigrade with 2 theta range from 40 to 42 degrees. And for the lattice Talmer analysis were done from lattice changes resulted from result analysis. This is the picture of the sample stage XRD that we use. And for the results and discussion, this is the result of the particle size characterization. From this characterization, we get the information that the corundum powder that we use has particle size range in micron with D50 value at 101.2 micrometer. This is the X-ray diffraction full profile. This profile matches the reference of corundum taken from crystallographic open database and from the reverse analysis of the full profile. And for the analysis at high temperature, we focus on peak with index Miller 104 because this peak is the first highest at lower angle to theta. So this is the result for peak position for index Miller 104. As we can see here that the position of the peak tends to moving to the smaller 2 theta degree of angle as the temperature increases. And here we can see the peak profile for index Miller 104. We can also see here that the full width half maximum for the peak also tends to be smaller as the temperature rising. This indicates that the crystallite size tends to be bigger during heating. And for the next slide, this is the result for the lattice value. So we compare our result with the result from Chick et al. And you can see here that the C lattice and the A lattice from our result were lower than the result from Chick et al. So the C per A ratio in our result become higher than the result from Chick et al. So we can also see that the C per A ratio from our result tends to increase as the temperature increases. This changes due to thermal expansion of the corundum. From this result, we can also get the information that the value of lattice parameter and CPR ratio for the type of crystal system of corundum is hexagonal. So we move on to the result of lattice changes due to thermal expansion. This is the result of lattice changes, and here we compare the result from calculation from the pattern that we get from the experiment and also the result from Schick et al. And we can see that the lattice change both for L lattice and C lattice determined from profile pattern show lower value compared to the result from calculation or Schick. However, the increased strength of the results from our experiment was similar with the results from and calculated, although the value is pretty much lower. And this characteristic shows that the sample that we use needs more heat to expand as much as the real and Schick result. And using linear regression, we get the linear equation for C lattice and L lattice as follows. And for the thermal expansion equation, we can see that thermal expansion equation is different for the C lattice and A lattice, and it means that there's an anisotropic characteristic on corundum. So in conclusion, that the X-ray diffraction of corundum was done at high temperature, and the results showed the changes in the structure of corundum, and it took heat as energy to change its internal structure. And the thermal expansion occurred during heating, resulted in the lattice parameter changes, and also according to particle size analysis, can be informed that the distribution of corundum particles is at micron size. That's all the presentation from me. Thank you very much for your attention. Wassalamualaikum warahmatullahi wabarakatuh. Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh. Okay, from the forum, I got some question from Dr. Kristanti Nurwidianingrum. Mrs. Garisa, why are measurements done in the range of 100 until 300 degrees Celsius? Can you explain? Please, Dr. Garisa.
Yes, thank you very much, Mr. Yudi. Well, Ms. Nanti, actually, we did the measurement at 100 and 300 degrees because the X-ray in situ apparatus is still in functional test stage. So actually, the apparatus can achieve 1,700 degrees centigrade, but because it's still in test, not functionally optimum not in optimum not we didn't, what is it? Because it's still in a test stage, so we didn't have we didn't do it until very high temperature. And then and our target at the with this activity actually is we want to see if the corundum is get the target of the heating with the heating of the apparatus, and the corundum is at the same level. Although there is a thermocouple in the apparatus. So because it's still in a functional test stage, so we didn't go further for the temperature measurement. Although actually it can be above 1000 centigrade. That's why. Thank you.
Okay. One more question from Mr. Teguh. When the data was collected, during heating or after reaching certain temperature? From Mr. Teguh.
Yes. Thank you for the question, Mr. Teguh. So we get the and we collect the data. So it's when we get when the temperatures reach the 100, we took the data, and then when temperature goes to 200, and we took the data. Like data was collected at after reaching the certain temperature that we set. So we can set in which, yes. To analyze the data, we did the Rietveld analysis.
One more question. What method did you use to analyze the data?
Yes, we did the Rietveld analysis for the data.
Okay, one more question from me.
Yes.
For corundum, as we know that corundum structure is hexagonal cross patch.
Yes.
Yes. In low temperature, for example, between 100 and 300, is this possible to make a phase transformation of corundum?
You mean it is possible to change it while?
Yeah, to change corundum phase in low temperature based on your X-ray analysis.
Yes, actually we didn't scan at the low temperature, so I'm not quite sure if whether it's ready or not. It can be done or not. So I don't think I'm not quite sure, Mr. Because we didn't do the characterization at low temperature.
Okay. Thank you, Mrs. Ganisa, for the presentation. So for the next presentation, we go to another topic from Cipto Sucipto. Mr. Sucipto, or the represents or who represent? Are you present? Okay, if no, we continue to the presentation from.
Yes. I mean.
Sorry. Yeah.
Sorry, Mr. Yudi, I'm in.
Oh yeah. Okay, Mrs. Talita.
Yes.
Can you start the presentation, please?
I have already sent the video to the committee. Can you play it? Yes, this one.
Okay, please.
Bismillahirrahmanirrahim. Hi everyone. Thank you for having me.
Today, I would like to present my paper under title Investigation of Layer Thickness and Diameter Distribution of PMW-CNTS by Image Analysis. The author consists of me, Talita Asimaria, Dr. Yudi Nugraha Taha, Dr. Nono Darsono. We are from Research Center for Metallurgy and Material LIPI. It will be presented on ISMM 2020 today at November 20, 2020. Carbon nanotubes or CNTS have outstanding properties and have been applied in a number of research scopes. The invention of CNTS at the first time leads to the further advanced studies such as single-walled carbon nanotubes and multi-walled carbon nanotubes. Doping multi-walled carbon nanotubes with phosphorus is nowadays a well-developed to form N-type doping carbon semiconductor. It was reported also phosphorus multi-walled CNTS exhibits quite promising material for electrochemical sensing application, especially for electroanalysis of absorbic acid, uric acid, and also dopamine. The shell and diameter structure of phosphorus multi-walled CNTS plays important role in their physical and chemical properties. To estimate these properties, it is usually visually using transmission electron microscopy or TEM. However, these methods are insufficient to approximate the variation of the cell and diameter structure in the wide geometrical area. Several researches also have been conducted by using image analysis and also its algorithm. However, the algorithm is found very complicated, and in this work, we propose shell and diameter measurement of phosphorus multi-walled CNTS using image processing techniques to simplify the process. So in here, we have two steps of method. The first one is data preparation and the second one is image processing. In the data preparation, we have ethyl alcohol, pyrazine, and 3-phenylphosphine that were purchased from Merck and were used as received without any further purification. The production of phosphorus multi-walled CNTS onto Si substrate was performed by direct liquid injection, catalytic chemical vapor deposition in combination with floating catalyst with cyclohexane as carbon source material and 3-phenylphosphine. For phosphorus multi-walled CNTS synthesized, the 10 ml ternary mixture of cyclohexane pyrazine was sprayed at 900 degrees Celsius through a searing pump with flow rate of 10 ml per hour. The acquired data from imaging modality of TEM was taken several times. Then we have 6 prepared images consists of 3 data for gravitic layer and 3 data for diameter distribution measurement. 3 data comprise of TPP concentration from 0.5%, 1%, and 2%. In the image processing, we have several steps. The first one is start, and we continue it into the image processing using JImage software from input data, binary mask, and also segmentation. Then we processing it again using MATLAB 2015 by having input data pixel thresholding, counting the gravitic lines, and then we do image analysis using SPSS 16. So in the image processing results, as you can see here, we have representative of TEM images of phosphorus multi-walled CNTS produced with various different TPP content. If you see the left picture from you, the A is the original images from diameter distribution measurement with content of 0.5% of TPP. And the B pictures is with content of 1% TPP and the C pictures with content of 2% TPP. Then we calculate the gravitic layer on the TEM images using image processing consists of binary mask and segmentation into size of 12 nanometer multiple 12 nanometer. So the representative of the refined binary images as shown below here in the picture A. This is the refined binary picture mask of multi-volt CNTS produced with the composition of cyclohexane in the presence of ferrocane catalyst with content of 0.5 TPP, the B pictures with content of 1% TPP, and the C pictures with content of 2% TPP. So in the image analysis, we have two types of demonstration. The first one, demonstration of the curve for measurement of graphitic lines, thickness distribution of phosphorus multi-volt CNTS produced from 0.5%, 1%, and 2% of TPP. It exhibits different thickness cell layer graphitic structure. So phosphorus multi-volt CNTS synthesized from decomposition 1% TPP produce higher thickness cell layer graphitic structure compared to 0.5% and 2% TPP. So based on the analysis on SPSS, the result indicates that TPP composition plays important role in catalytic activity, the growth of graphitic layer in the phosphorus multi-volt CNTS structure. The second analysis is demonstration of the curve for measurement of diameter distribution of phosphorus multi-volt CNTS produced from 0.5%, 1%, and 2% TPP. It exhibits different diameter tube distribution. As you can see on the graphic, phosphorus multi-volt CNTS from the composition of 2% TPP produce more homogeneous structure compared to 0.5% and 1% TPP. So this result indicates that homogeneous structure of phosphorus multi-volt CNTS can be synthesized by adjustment of doping source material concentration. From the work we do, we can have conclusion that the effect of 3-phenylphosphine, or we can say as TPP, on the distribution of carbon layer and size of phosphorus doped multi-volt carbon nanotubes, or we can simplify as P multi-volt CNTS, were investigated by combination of transmission electron microscopy or TEM and image analysis. The phosphorus multi-volt CNTS were synthesized by direct liquid injection catalytic chemical vapor deposition with floating catalyst through the composition of cyclohexane and 3-phenylphosphine from 0.5%, 1%, and also 2% of TPP in the presence of ferrocene catalyst on silicon wafer substrate. Phosphorus multi-volt CNTS fabricated by the composition of 1% TPP produce higher thickness cell layer graphitic structure compared to 0.5 and 2% TPP. Phosphorus multi-volt CNTS that fabricated by the composition 2% of TPP produce more homogeneous structures compared to 0.5% and 1% TPP. These results demonstrate that TPP composition plays important role in catalytic activity, the growth of graphitic layer, and also tube diameter distribution in the phosphorus multi-volt CNTS synthesis. And finally, the author would like to say thanks to Indonesian Institute of Science for research and also publication funding. Thank you.
Okay, I got one question from audience, Mrs. Talita. Mrs. Talita, is this method applicable for layer thickness measurement, for example, graphite material or several layer of graphene?
In my opinion, yes, we can do the layer thickness measurement for this method into graphitic material or also for layer graphene. But it depends on the image that you have, because the image that I got before, I need to do image processing for several steps before we calculated the graphic. Thank you.
One more question, Mrs. Talita. How you distinguish the carbon nanotube and impurities if carbon nanotube contain much more impurities in your measurement?
If you see my picture when we got the picture on TEM, you know that the line that having bulk, more thickness, the color of black more thickness rather than the surrounded area, it will contains more CNTS rather than other area. So by that point, we try to do segmentation for those area that having more CNTS. Thank you.
Okay, is there any question from the forum? Okay, if no question, we continue to the next presentation. Presentation from Dr. Murni Handayani. The title is Graphene Oxide-based Nanocomposite for Screen Printing Carbon Electrode Modified as Electrochemical Biosensor for Cephexim Detection. For Dr. Murni Handayani, please, the time is yours.
Yeah, good afternoon, everybody. I have already shared my PowerPoint slide. Is it already open for all? Hello?
Yes, yes, we can see the screen.
Okay. Wait a minute. I cannot see my. I'm sorry. I cannot open from the full screen. I try again. Yeah. Okay. Good afternoon, everybody. I would like to present my research about graphene oxide-based nanocomposite for screen-printed carbon electrode modification as electrochemical biosensor for Cephexim detection. And this result is because of the collaboration between Research Center for Metallurgy and Material with ITB in Lab on Chip group. And the outline of the research is introduction and then methodology and result and discussion, and after the conclusion. This is the introduction. We know that carbon-related materials such as graphene with its derivatives and fullerenes, carbon nanotube have presented remarkable properties for their use in nanotechnology-based nanodevices. Then carbon-based electrodes are widely used as working electrode in electrochemical sensors due to its characteristics such as low background current, high electrical conductivity, and wide potential range. And from this image, we can see that for glassy carbon, carbon nanotube, nanofibers, nanowires, nanocoils, diamond, graphite-based, graphene oxide, reduced graphene oxide, and graphene itself are also common for use for material as a working electrode in electrochemical sensor. And especially for the graphene oxide is promising material for electrode development due to its superior properties because it has low cost, easy access, and widespread ability to convert to graphene. Graphene oxide is graphene with the hydroxyl and epoxy group decorated in its plane consists of only triagonally bonded sp2 carbon atom, and it's perfectly flat. But in other hand, graphene oxide containing more sp3 than sp2 carbon, and it causes graphene oxide has a smaller conductivity compared to the graphene, pristine graphene. So we have to make modification of the graphene or oxide surface to get the better of the conductivity and also other properties. And for the cefixime detection, cefixime is the orally absorbed antibiotic which is used for the treatment of mild and moderate bacterial infection, such as otitis media, pharyngitis, gonorrhea, and bronchitis. And degradation of this cefixime under storage condition can change in physical and chemical characteristic, which cause undesirable side effects. So this is possibility for us to detect of this cefixime, because this will make us harmful if the cefixime inside in our body and also in the environmental detection for this is very high, and therefore specific analytical procedure for the determination of cefixime is required. And the cefixime has been studied and investigated by many techniques. We can see from these images that there are several techniques we can use for the detection of the cefixime, such as spectrophotometric, fluorometric, high performance thin layer chromatography, and also cyclic voltammetry. And among of all these techniques, cyclic voltammetry is the fastest and also non-expensive techniques for the detection of cefixime. For the previous research, I have already tried to find many reference for the detection of the cefixime, and it's very limited for this research using graphene oxide. And I found one of the articles about electrocatalytic oxidation behavior of cefixime antibiotic using carbon nanotube modified in glassy carbon electrode, not using SPCE. But because multi-wall carbon nanotube also in the nanoscale and also has exceptional performance of the conductivity, and we can see here that there is a good conductivity and also reduction and oxidation for the sensing applications. And we can see that many techniques we can get from this review of previous journal. That's the DPP and using many electrodes, but there are no application of the graphene oxide reported yet for the electrochemical detection of the cefixime. So that's why here we are focusing. We are focusing on the research of the modification of graphene oxide for cefixime detection. And this is on the graphene oxide. We then doing modification using the iron and also strontium nanoparticles, and we then use this nano composite for surface modification of the SPCE, like in this image. This is the roadmap of the research. The first is synthesis of graphene oxide, then fabrication of graphene oxide-based nanocomposite, and then we modification of the SPCE. Then we apply for this graphene oxide-based nanocomposite on the SPCE for the application in cefixime detection. This is the methodology. The first, we did for synthesis of graphene oxide using the usual method. There is a hammer methods, and then after that we synthesis of graphene oxide based nanocomposite. After that we prepare for graphene oxide modified of SPCE. Then we prepare of the cefixime sample, and before that we have to characterize our graphene oxide using XRD, SEM, and ADX, and then we characterize also using for the nanocomposite using XRD, SEM, and ADX. And after we confirm that we get our material, then we cast our nanocomposite. Then we do for the electrochemical using GV measurement. This result and discussion, we can see here from XRD result of the graphene oxide, And for the crystal structure analysis of graphene oxide by using XRD, it is shown that graphene oxidation occurs. The sharp diffraction peaks were observed around 10.66, and interlayer distance is about 0.82 nanometer, and no diffraction peak of the pure graphite. If we see around 26, this means it's pure graphite, and it's disappear here. So this means we get the successful result of the graphene oxide. And this is also the analysis of the SEM of graphene oxide, the morphological structure of the surface of graphene oxide, so that it's a very typical image of the surface of graphene oxide, and the seed and wrinkle areas of the SEM results. So the very good agreement. Another analysis of the graphene oxide using UV-Vis, and then also we combine the reference with our previous work that we compare with the graphite, graphene oxide, and then nanocomposite for the XRD. It's very clear that we got our result of the graphene oxide, and then for UV-Vis measurement, the spectrum here we can see that's one very sharp peak around 232. This is due to from the transition for pi asterisk transition of the aromatic CC bond. And it's very clear this is very typical of the graphene oxide peak. The same ADX analysis for the graphene oxide when compared with the nanocomposite, we can see from this image, and it's shown that I'm very sorry, this very small maybe and cannot be seen clearly, but from this image we can see that it's for the graphene oxide is very typical, and then after adding for the iron nanoparticle, it's so here.
Dr. Murni, 2 minutes
Yes?
remaining.
Okay. And then also it's all give a difference between the graphene oxide with nanocomposite, and here for the ADS we can see that is also clear. This is Fe, and this is C, this is O, and this is strontium, this is C and O. So this means we got our result for the nanocomposite, and this is the UV-Vis measurement of the graphene oxide based nanocomposite. We can see that there is a redshift in the higher wavelength, and it confirmed from the nanocomposite of our samples. This is the cyclic voltammetry analysis for the SPCE modified of the graphene oxide nanocomposite. We can see when we use the PBS, then it's also for the reduction and oxidation peak. But when we give the Cefixim, it's then become very clear that our nanocomposite will give like FAGO and strontium graphene oxide give a very significant response for the electrochemical properties. And this is for the stability analysis, SPCE with modified graphene oxide nanocomposite. The graphene oxide modified SPCE gives the drop stability around 50.9%, and modification with the iron nanoparticle and strontium nanoparticle for the strontium is give the best stability because the dropping value is only for 0.81. And this is the conclusion. The graphene oxide was successfully synthesized by hammer technique, and the result was analyzed by XRD, UV, SEM, ADX analysis. The obtained graphene oxide was used for making the modified graphene oxide of the iron graphene oxide and strontium graphene oxide on SPCE. Then the performance of sensor with surface has been modified. Then we measure by cyclic voltammetry, get a successful result, and the result of testing of Cefixim give the result that SRHGO give the high stability. That's all. Thank you very much for your attention. Yeah.
Okay. Is there any question from audience?
I'm sorry, I didn't start my video.
There is one question.
Okay.
What is the meaning of nanocomposite on your research? Which part of nanostructure have you proved?
Yeah, actually, I proved by my nanocomposite using the SEM only for this. You can see here. The meaning of the nanocomposite in my research is we give the nanoparticle on the graphene oxide surface. So based on this, we have to prove by using TM measurements to see the nanoparticles on the graphene oxide surface to prove and to confirm that we get the result. But because the time is limited, then we don't get for the result yet for this TM measurement result. But for the DCM, we can see here that the significant difference between the surface of the SEM result between graphene oxide with the nanocomposite, we can see from this image. From this image, it's so different when we give the iron nanoparticle on the graphene oxide surface. We can see that there is several particles of the iron. Actually, we have to also give the mapping area each element for the iron KO and also strontium KO. And we will do for further measurement because this is just a preliminary research for us for the next develop of our sensor for the traffic sim. For the next measurement, we can then include for complete characteristic using TM, SEM, and then mapping of SEM ADX to know the elemental analysis. But we can now see from this surface of the graphene oxide on the SEM that's really different when we give the iron and also strontium. I hope this will answer your question, Mr. Yudi or moderator.
One more question
yes.
from me.
Yes.
You mentioned that you use this material for traffic sim sensor. Can you explain how about the sensitivity of sensor and the limit detection of this sensor?
For the limit detection for the sensor, we didn't measure for the chronoamperometry yet because this is just the preliminary result of our work. But we can see here that when we use the two measurement using the analysis of the cyclophotometry, this is in twice of the two cycles experiment, we can see for the GO and also SNGO, it's more stable compared when we use FEGO because there is a magnetic properties of the FE that can give effect for the electrochemical properties. And we can see from the second cycle of the cyclophotometry that it make flat on the oxidation or anodic part. Maybe we can see in the middle part of this FEGO. But for other, when we use for more than one cycle, it's still stable. We confirm by this measurement. And we measure for the value of the dropping value using the cyclophotometry. That's GO give around 50.9%, and then FEGO give the 77.5% based on the cyclophotometry. But strontium GO has the best stability because when we did for the cycles, second cycles, it only dropped around 0.81%.
Okay, we have 1 minute. Is there any question from audience? Okay. Okay, if no, we finish the session. So we go to another session. Dr. Murni will be next moderator for this next session. So
okay, thank you very much.
For Dr. Murni, please.
Okay. So this means I can directly to be a moderator in this session?
Yes, of course.
Okay.
Because in this schedule, as well as schedule.
Okay. Thank you very much for the time for me to be a moderator in this session. I'd like to firstly to open this session for the paper in this session. The first is from Miss Annie Febriana about a simple approach of synthesis of graphene oxide from brook graphite. Hello, Miss Annie Febriana. Will you keep presentation directly or by recording audio or video?
By recording video.
Okay,
that I
so
have sent to the committee.
okay, yeah, this committee will open your recording lecture.
I'm from Research Center for Methodology and Materials, Indonesian Institute of Sciences. Today, I would like to present my research about a simple approach of synthesis of graphene oxide from pure graphite with the focus of discussion on time steering duration variation. The outline that I would present consists of introduction, methodology, result and discussion, and the last is conclusion. Introduction. Graphene is a single-layer carbon atom in two-dimensional honeycomb lattice. Graphene is increasingly attached so much attention to the scientific and engineering world because of its fascinating properties in electrical, mechanical, thermal, chemical, and optical properties. It's very thin material in size of nanometer, but have 100 times stronger than steel. These unique properties make graphene be a promising material for advanced technology for many applications like sensor, nanocomposite, biomedical, hydrogen storage, etc. But it's difficult to synthesize graphene in such large mass production. The most common synthesis method like Bradystaudian-Meyer method and Hammer's method. But this method can cause hazard and toxic with the use of chlorine dioxide and nitrogen dioxide. By this method, graphene oxide is synthesized treating graphite powder with phosphoric acid, sulfuric acid, and high quantity of gallium permanganate. As we know that gallium permanganate is explosive material. In this research, we try to prepare graphene oxide in easy way, cost-effective by using convenient method using graphite with gallium permanganate by variation of steering duration. Moreover, reduction of graphene oxide was carried out using aluminum powder to produce reduced graphene oxide. This is the experimental method we did in this research. The chemicals used during the process are pure graphite powder, gallium permanganate, sodium nitrate, sulfuric acid, hydrogen peroxide, hydrochloric acid, and ionized water. The experiment consists of 3 steps: synthesis of graphite oxide, synthesis of graphene oxide, and reducing the graphene oxide. The detail of each step we'll discuss in the next slide. Result and discussion. First, we did visual observation for all the product of almost step. Synthesis of graphite oxide. First, we mix the sodium nitrate and sulfuric acid and stir them in an ice bath to get temperature under 20 Celsius degree. Then we add calcium permanganate and graphite powder and continuing the stirring for 2 hours. So the color of the mixture will change to dark green. Then the ice bath was removed and the temperature was raised up to 40 Celsius degree. The variation of stirring duration we set for 3, 5, 7, and 14 hours until forming brown paste. For the stirring of about 3 hours, we don't get the paste because stirring time is not enough to make the sample fully oxidized. The longer the stirring time, the more paste we get. But if the reaction over-oxidized, the solution doesn't form a paste. That means that the stirring time should not be more than the time it oxidized. After add with the ionized water and stir the solution for 30 minutes, we add some hydrogen peroxide and the ionized water sequentially until the color of the solution changes to yellow. The adding of hydrogen peroxide is to consume the residue of calcium permanganate. The color change indicates that the high level oxidation of graphite powder. The solution is then filtered washed with using 1 molar hydrogen chloride and deionized water until pH becomes neutral. The solid product was then dried to get graphite oxide. From graphite oxide, we synthesize the graphene oxide. Graphite oxide was grinded using mortar and pestle and then sonicated for about 30 minutes with the ionized water as medium. This is the figure of the product after sonication. The solid product was then filtered, washed, and dried to get graphene oxide. The last step is reducing graphene oxide. We did the experiment using aluminum powder as a reducing agent. Graphene oxide and deionized water was sonicated for 2 hours. After that, we add hydrogen chlorides and aluminum powder to the solution. Stir the mixture with spatula, then let it stand for 30 minutes. This is the figure of the product. The color of the result is black, maybe due to the increasing of hydrophobicity of the material caused by decreasing of oxygen in the graphene oxide. After that, add 1 molar hydrogen chloride solution to remove the remaining aluminum, and the product was then filtered, washed, and dried 40 hours to get reduced graphene oxide. Move to the same analysis. This is the micrograph of CO6 graphene oxide with 7 hours stirring and CO7 graphene oxide with 14 hours stirring at the magnification of 25,000 times. We can see that there is a perfect structure-like response. The result indicating that graphite has been exfoliated during the oxidation process. The white image indicates that graphene oxide is containing graphene chip. At the magnification of 40,000 times, the thickness of the layer graphene is about 11 to 40 nanometer, which means that it's still far away from the single layer graphene that should be about 2 until 5 nanometer. Maybe it could be helped when we use TEM analysis since it has more accurate. EDX analysis. The EDX spectrum, so P corresponding to CO6, consists of carbon, oxygen, and sulfur, with mass ratio of carbon to oxygen is about 60 to 40, and atom ratio of carbon to oxygen is about 66 to 30. And for CO7, the spectrum for carbon, oxygen, sulfur, and mangan with mass ratio of carbon to oxygen is about 60 to 34, and atom ratio carbon to oxygen is about 70 to 30. The presence of sulfur that was come from sulfuric acid, and the mangan was come from the calcium permanganate that used as oxidizing agent. So this might be the oxidation process is not well occurred, but this also confirms that graphene oxide was actually formed since there are carbon and oxygen. Other characterization is using UV spectra. From the graph, we can see that the peak intensity of graphene oxide increased with reaction time from 3 to 14 hours. This suggests that enough time is required for higher degree of oxidation. However, if the steering time goes up until the absorbance peak getting decreased, this might be result of over-oxidation. The UV visible spectra of graphene oxide showed an absorption peak at wavelength 240 nanometer. But after reduction by aluminum powder, the peak of reduced graphene oxide was shifted to 210 nanometer, suggests that the electronic conjugation within graphene sheet was a little bit defect. FTIR analysis. From the FTIR analysis, we can see that there is functional group of carboxyl, carbon and carbon bond, and carbon and oxygen bond. And from XRD analysis, we can see that after oxidation process, the diffraction peak of sharp and high intensity of graphite is absent. Meanwhile, the diffraction peak of graphene oxide at around 10 degrees is appeared. Furthermore, there is a diffraction peak at around 43 degrees in XRD pattern of graphene oxide, which indicates that graphene oxide exhibits turbostratic disorder. Conclusion. From the discussion before, we can conclude that graphene oxide, and reduced graphene oxide was obtained using convenient method by treating poor graphite with using calcium permanganate and sulfuric acid as the oxidizing agent and sonicating the solution to separate the layers of the graphite. Graphene oxide, and reduced graphene oxide were characterized using SEM, UV spectra, XRD, and FTIR spectroscopy analysis. Graphene oxide with steering time 7 hours was already good to obtain the layer of the graphene oxide.
Serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia, infrastruktur riset strategis, dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim,
So we have to use like TM and in high
Ketahanan
vacuum TM to get like very good image for the layers of the graphene. Thank you so much, Dr. Andri, for your comment. And
Yes,
this is
yes.
very good for us.
Yeah.
Thank you.
Thank you for the answers, and I think it's a good research.
Yes. And also because time is up, so I like to move to another paper for second one. It's about a study of reduced graphene oxide reduction degree to methanol sensing performance, will be delivered by Biaunik Kumila.
Yeah.
Hello. Yeah.
Thank you for Ibu.
It's yours.
Yeah.
Yes.
Thank you, Ibu Murni, for the time. My name is Biaudik Kumila. I'm from Department of Physics, UIN Syarif Hidayatullah. Here, I would like to present my research with the title of Study of Reduced Graphene Oxides Reduction Degree to Methanol Sensing Performance. And here is the outlines of my presentations. First is backgrounds, objectives, introduction to reduced graphene oxide, experimental section, result and discussion, conclusion, and future research suggestions. And this is the big background of my research. In the sensors field, we face several issues according
I'm sorry,
to the...
can you use F5 or make a full screen for your presentation screen? Because it's still very small. Okay.
Is it full screen already?
Not yet.
Really?
Because the screen doesn't move. So, or maybe you can continue for your presentation and try. I don't know for other participants here. Can you get for the full screen for this presentation slide?
Not yet full screen, actually.
Okay, the same.
Maybe I
Yeah.
click.
Okay,
Yeah.
okay, it's working now.
Okay, yeah.
Okay, you can continue.
Yeah, thank you. So here is the backgrounds of my research. In the sensors field, we face several issues. We are struggling to make a very high sensitive and selective sensors with the fast response and recovery time, and also make simple handling and low cost process. And also the previous works about the graphene sensing, they are lack of sensing mechanism study in order to deep understanding to enhance the sensitivity. So this is the objectives of my research. First is study the effect of reduction degree to methanol sensing performance, and then to propose and study the sensing mechanism. This is the introduction to reduced graphene oxide. And before we move to the reduced graphene oxide, first we discuss about the graphene. Graphene is amazing materials with physical and chemical properties such as high mechanical strength, high specific surface area, highly sensitive to electrical field, high carrier mobilities. And due to its amazing properties, the graphene has been widely used in some applications, such as stem cell based tissue engineering, supercapacitors, and biosensors. And the difference of graphene oxide, and reduced graphene oxide is shown in this figure. Graphene has no oxygenated functional groups, lead to the highly conductive materials, and we can oxidize the graphene, become the graphene oxide through some chemical reactions widely by the Hammers method, and with the raw material of graphite. And the graphene oxide has a high oxygenated functional groups, low conductivity. And for reduced graphene oxide has a sufficiently high oxygenated functional groups and higher conductivity compared to graphene oxide. And this, we move to the experimental section. We prepare the graphene oxide by Hammers method, and we prepare the reduced graphene oxide thin film by spin coat. First, we spin coat the graphene oxide solution on the SeO2 substrate, and then further perform the thermal reduction at various temperatures at 230, 350, 500, and 850 degrees C for 2 hours in vacuum, around 10-3 torr. And then to prepare the sensor device, we perform the metal deposition, which is nickel and gold, on top of the reduced graphene oxide. And we did the characterization and measurements, such as scanning electron microscope, SEM, Raman spectroscopy, X-ray photoelectron spectroscopy, X-ray diffraction, and also electrical property measurement and gas sensing measurement. And this is the scheme of gas sensing measurement. We put the device on top of the simple closed glass cube, and we are connecting the wire to, we are connecting the metal to the source matter, and then let the methanol to evaporate, let the gas to evaporate, and the sensing is working, and the signal is displayed by the computer. And here is the SEM images of graphene oxide and reduced graphene oxide at various reduction temperatures. The brighter region in these images corresponds to the wrinkle layer or folded layer of graphene, which is formed during the thermal reduction. And at severe thermal reduction at 850 degrees C, the porous-like structure graphite materials is formed, which is indicating the breakout of carbon-carbon bond or breakout of graphene. And this is the high resolution of C1S spectra of graphene oxide and reduced graphene oxide at different reduction temperatures. From these images, from this graph, we can conclude that the amount of oxygen moieties decreases after thermal reduction. And we can clearly read the result from XPS analysis using this graph. This graph is the CO area ratio as a function of reduction temperatures. From this data, we can conclude that CO ratio increased along the thermal reduction up to 500 degrees C due to the evaporation of remaining solvent and restoration of sp2 carbon. And but after thermal reduction at severe temperature, which is 850 degrees C, the rapid decrease of CO ratio is seen due to the carbon reoxidation and carbon decomposition And B is the carbon-carbon bond recovery as function of reduction temperatures. And we can conclude from this graph that sp2 fraction was recovered along with the increasing thermal reduction temperatures. And here is the Raman spectra of the sample. And we can see from this graph that the D peak corresponds to the sp2 carbon, and G peak corresponds to the defects present on the graphene, and IG is decreased after the thermal reduction up to 850 degrees C. That is due to the removal of oxygen moieties after thermal reduction. And this point, IG is rapidly increased due to the carbon decomposition and formation of structural defects such as porous and vacancies.
2 minutes left for presentation. 2 minutes left for presentation.
Oh, yeah. Okay. Yeah. So next, those data, I mean, is in agreement with the SEM images. And this is the XRD pattern of RGO and RGO at various degrees of temperatures. And we can clearly see, this is the table of the calculation of the spacing. We also do the microstructure evolutions after thermal reductions. And this is the electrical property of graphene and reduced graphene oxide, and it implies that the conductance of GO gradually increase along with the increasing reduction temperatures. And then we also do the electric transport measurements, and it concludes that the RGO is a p-type semiconductor with a Hall mobility of 25.9 centimeters square per volt second. And then this is the sensing performance, and we can clearly see the result of a sensing performance by this graph. The methanol sensing performance is increasing along with the increasing amount of increasing amount of oxygen moieties groups or decreasing amount of sp2 carbon. And we also test the acetone sensing on a 50 ppm, and the sensitivity is 0.82%. And this work compared to the previous work by Alexei Lipatov at 2013 has a higher sensitivity for the methanol at 50 ppm. And we also propose
time is over. Can you can you do faster more?
Yeah. And we also propose the mechanism of detection. Simply say that if we work with the open shell adsorbents, so we need to increase the amount of sp2 carbon, and for the closed shell adsorbents, we need to enhance the sensitivity. We need to simply say we need to top up the amount of oxygen moieties. And also the sensitivity of the sensing is depend on the polarity and molecular size. The higher the molarity, the higher the sensitivity, and the higher the smaller the molecular size can penetrate deeper through the graphene oxide layers, leading to the higher sensitivity. So the conclusion is thermal
maybe
reduction.
Maybe we have to stop for the
okay.
We just get
Okay, thank you
I'm very sorry because that is already over. We open for the just 1 minute left. We offer for the question, or only one question, please. If not, then I have a question. Did you do for the XPS in Indonesia or in another country? Because we don't have, I think, in Indonesia for XPS for the measurement for this graphene.
Thank you for the questions. Yeah, I performed the XPS measurement in the Taiwan because, yeah, this is the research. The research is I did this in the another country.
Okay. Actually, so many questions from myself, but maybe next time when can discuss. Okay, we have to move for another paper. Thank you very much for your presentation. Yeah, we move to another paper from Ms. Latifa Isna.
I think Miss Latifa is not present, so we can continue to
Oh, really? Okay.
Miss Adinda.
Okay, thank you for your confirmation, Mr. Farid. Yeah, we move for for Miss Adinda Adani. Hello. Okay. Okay. Would you like to perform your presentation live or by recording lecture?
By record.
Okay. May I ask the organizing committee to open for the recording? Have you already given to the committee?
Miss Bernick, can you stop share?
Yeah. Miss Bernick, can you stop for the share screen?
Ini Mas, lihat aja nih Mas Daniel nih.
Hello.
Hello.
Okay. Time is yours, please.
Bismillahirrahmanirrahim. Thank you for the given session. But you can see our screen. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Let me introduce myself. My name is Adina Adani. I'm from Syarif Hidayatullah, Jakarta. In addition, I would like to present about our research by title Analysis the Increase of Nickel Substitution on Crystal Structure and Magnetic Properties of Lanthanum Barium Manganate Material. Our presentation consists of 4 parts, starting with an introduction and background of the research methodology, which is the flow of research, and then follows the result and discussion, and the last part is the conclusion. The high demand for human needs from time to time is a reference from the developing technology currently, which increasingly more sophisticated, thus making research to material engineering so that it could be applied to the latest technology device. One of the materials that have attracted attention for material engineering is perovskite lanthanum manganate, because its magnetic and electric properties, which are magnetoresistance, where the material will experience change in electric resistance when given an external electric field. This property can be applied as a data storage, magnetic sensor. In recent years has been developed as a material absorber. Lanthanum manganate is a derivative of perovskite AbO3, where set A is filled with lanthanum and set B is filled with mangan. In 1950, Jonker van Santen researched on lanthanum manganate material by substitution divalent ion at L sites such as calcium, barium, and strontium. And he reported that lanthanum manganate was ferromagnetic at low temperature and was antiferromagnetic at room temperature. The substitution of the valent ions at the La site increased the Curie temperature and magnetic properties, where the Curie temperature is the best transition temperature in the material from ferromagnetic to paramagnetic. In the study, the Curie temperature lanthanum barium manganate oxide was produced at the composition X is 0.33, which is about 340 Kelvin. Temperature Curie with the same composition and the same temperature was also reported by Chu et al. In 2000. This makes the reason that the basic material used in this study is perovskite lanthanum barium manganate. In 2013, City et al. Conduct material engineering by substituting nickel at the mangan site in lanthanum barium manganate oxide material with a composition 0 to 0.06. Based on the result of his research, she reported that along with increased the composition of X, it can decrease the magnetic properties and is very potential as an absorber material. In 2018, Harrod et al. Research of the same type as a City et al., but with a large X composition, and X is 0 to 0.075. Based on the result of his research, he reported that along with increasing the composition of X, the temperature of the Curie could decrease. So far, no study have reported the structure and magnetic properties of perovskite lanthanum barium manganate nickel oxide material with a composition more than 0.1. So this attract me to do the research. On this slide, there are two hysteresis curves A and B. A is the hysteresis curve of lanthanum barium manganate oxide material from the research of Prio et al. The difference between the lines before and after the valent ion substitution of barium at site LR. This indicates that there is change in the magnetic properties of the base material from previously paramagnetic to ferromagnetic. This change in property occurs because the substitution of the valent barium ion at LR site causes the mangan ion to have two different valence, namely mangan 3 plus and mangan 4 plus, so that a double exchange interaction occurs. So the double exchange interaction is an electron exchange interaction between two different ions because of the substitution of other ions that cause distortion in the structure of the material. And figure B is the hysteresis curve after the presence of substitute nickel element at the mangan sites of the lanthanum barium manganate material, which is the result of the research by City et al. With the presence of nickel, it can reduce the magnetic properties of the base material. This is because the presence of nickel can reduce the mangan 3 plus ion so that the double action interaction will be reduced. This research consists of several stages, namely sample synthesis using the salt gel method, characterization sample using XRD and VSM, and then the results of the characteristics are analyzed data. High purity base material has weight according to the result by stoichiometry formula. Mix all precursor dilute nitrate base and then homogen with a stirrer and heat at a temperature of 353 Kelvin and ammonia at the pH 27. The gel was had to be dehydrated at 453 Kelvin 40 hours until the dry gel was obtained, and then calcination at 873 Kelvin for 8 hours for the decomposition of organic compounds into the sample during the synthesis process, and sintering at 1123 Kelvin for 10 hours for fast formation of crystal growth and strength crystal bond. And then all samples were characterized using XRD. Then data from the results of XRD was analyzed using the retrieval refinement method on GISA's XPGUI. So varied output that result from this process which obtain information about phase, crystal structure, lattice parameter, and volume. The magnetic properties were known based on the results of VSM. With output, the hysteresis growth with the comparison between the magnetic field and magnetization. Now is the result indication. So in this slide is the diffraction pattern characterization of XRD. It can be seen that when X is 0 to 0.2, a single phase is formed, which is indicated by the absence of peak addition due to the nickel substitution at the mangan state. In contrast to the case when X is 0.3, there is an additional peak in the diffraction pattern at an angle of 23.86 degrees, which indicates a fluorescent phase has been formed, which is owned by barium manganate oxide phase. And figure of diffraction peak of sample at high intensity. It can be seen that in general there is a shift the peak of the diffraction pattern toward a larger theta. This occurs because of the radius of nickel 3 plus that substitutes smaller than the radius of iron mangan 3 plus, which is 0.56 angstrom and 0.58 angstrom. This is accordance with the Bragg law equation, which show that a larger theta value will be generated if the distance between the crystal planes has a small value, resulting in a smaller lattice parameter value. So this is the result of the refill refinement of lanthanum barium manganate nickel oxide on GISA's XPGUI. It can be seen in the following figure that there is a match between the calculated diffraction pattern in green line and the observed diffraction pattern in red line. This plot also produces an error curve in the form of a pink line, which is the difference between the intensity of the observation and the calculation. The result indicate the calculation data with observation data have a good fitting and can be accepted. From the analysis from GISA PGUI with retrieval refinement method, it can be seen that the parameter structure for its composition can be seen in this slide. It can be seen that along with the increase in the composition of X doesn't change the crystal structure of the basic material. This result is supported by the calculation of Goldsmith's tolerance which is the value of the stability of the perovskite structure after ion substitution at site A or site B with the following equation, where in this study the value, the Goldsmith tolerance factor of 0.196 is included in the range of the rhombohedral structure. In general, the lattice parameter value decrease, which of course will directly contribute to the decrease in the unit volume cell. Based on the results of the XRD characterization of the sample, we can find out the crystal size calculated using the scalar equation as follows, and the value generally decrease. The decrease in lattice parameter, volume, and crystal size because of the radius of nickel 3 plus that substitutes smaller than the radius of ion mangan 3 plus, which is 0.56 angstrom and 0.58 angstrom. This decrease was also strengthened by a larger shift of the diffraction peak move toward a high angle. And then this is the analysis result of sample characteristics using VSM. It's clear from the historical curve that the increasing of the X composition will result in a sloping historical curve, which indicates that there is a decrease in magnetic properties. This decrease in magnetic properties is supported by a decrease in the value of saturation, susceptibility, and the probability of interaction between Mn3 plus and Mn4 plus, in which there is a double exchange interaction. The decrease in double exchange interaction occur because the presence of substitute nickel 3 plus and the mangan sets cause a decrease in the number of mangan 3 plus ions. That the presence of nickel 3 plus cause the emergence of the new interaction that are antiferromagnetic, which of course directly contribute to weakening the magnetic properties. Well, so that overall in the study can be concluded as follows. In conclusion, lanthanum barium manganetical oxide has been successfully synthesized using soil gel method. The substitution of nickel for X is 0 to 0.2 from a single phase with a rhombohedral crystal structure and R3C space group when X is 0.3 to phase were formed, and one of them is the barium manganate oxide phase with rhombohedral crystal structure and R3M space group. The substitution of nickel 3 plus doesn't cause structure change, but there are changes in lattice parameter, volume, and crystal size are decreased. The result of VSM characterization of lanthanum barium manganetical oxide, along with the increase of X value, which can weaken the magnetic properties on the material, which produce the decreasing value of magnetization and susceptibility. So, thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Ms. Adinda Ardani, for your nice presentation. I open for the question in this discussion time. Is there any?
Hello, Bu Murni.
question?
Can I ask
Yes.
directly?
Okay, please. Time is yours, Mr. Deni.
Okay. Halo, Adinda.
Hello.
Ya, salam for Ibu Riri ya.
Yeah.
Okay, it's good job. But there are some mistaken from your XRD analysis, but it's okay. Maybe this is due to the typo. From your data, from your PPT slideshow, it's on WRP. It should be RWP. Okay, maybe you cannot see because it's already in the video. But if you have the slide PPT, the symbol of the WRP, it mistaken, should be RWP. Okay, next, maybe later you just note, and then later you just make correction. And from your XRD result, it seems there are some additional peaks. It seems not pure all the perovskite phase from your result. Or I don't know, due to your rate field analysis not so good. I don't know whether due to your analysis or due to the nature of your materials. Okay, but as I can see from the data, the intensity is only 10 power 2 is not so high, right? For my result usually thousands, 10 at least 1,000, 10 power 3 or more the intensity. So it means your soil gel processing not so pure in my view.
I have a bad signal. Can you repeat your question?
Okay, for the XRD.
Maybe slowly for your speak, Mr. Deni.
I can give some comment for your XRD. Okay, the XRD for the perovskite is what we call typical. For all perovskite oxide material is typical, even though the A side or B side is different, but the number when we scanning from 20 to 80, the total number of peak is same. Okay, but from your result, XRD result, there are some additional peak other than the normal total peak that it should be. Can you understand what I mean?
Yes.
Inshallah.
Okay. Inshallah. And then they are mistaken of the symbol of the XRD result. It will be RWP. RWP, Mbak. Not WRP. Okay. They are in the table. There is in the table about the data analysis of the XRD result. Okay. That's my comment for the point number 1. And then the number 2. Okay. From your data, you already showed the Goldsmith tolerance factor. It's good. Okay. And the result also almost 1, meaning the perovskite is almost cubic. Okay. It's good. Good job. And then my next question is, why did you choose the B side variation other than the A side one? What is the reason? Okay, maybe it's enough, Bu. Yeah.
For the second question, will you give answer, Miss Adinda?
Yeah.
1 minute left, less than 1 minute.
I chose this composition because based on previous research by City et al. In 2017. And I can say this is perovskite structure because I have a value of tolerance Goldsmith in range 0.9060 to 1.
It's okay. That one is okay. I didn't comment about your tolerance factor. I just comment, why did you choose the B side variation of your perovskite material other than the A side? Maybe you want to achieve something. You didn't change any A side, right? You only changed the B side of your perovskite. Why?
I just based on previous research.
Okay. So you don't know the reason, huh? You just follow the previous one. Okay. It's okay. Just say hello to Ibu Diri from me. Okay.
Okay, maybe this
Next
is for
you should know the reason, huh?
Yeah. This is homework for Miss Adinda from Mr. Denny. Yeah.
Okay, thank you.
Yeah, thank you very much, Mr. Denny, from your very nice suggestion and also good comment for research of Miss Adinda. This is very good for the next improvement of her research. And because the time is up, so we stop for this session and we will have a break session for 50 minutes. And yeah, we will have 15 minutes around 3:15 we will enter again for this session. Thank you very much, and I will have to stop the session and see you again 15 minutes later.
Berawal dari cita dan asa untuk membangun negeri, memberikan segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah Kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah Kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM pendukung IPTEK di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka konservasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia, infrastruktur riset strategis, dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi, material maju, energi, teknologi, informasi dan komunikasi, pertahanan dan keamanan, dinamika sosial, kemanusiaan dan kebudayaan, kebencanaan, inovasi teknologi dan pendayagunaan IPTEK, pelayanan, pengujian dan pembinaan ilmiah, serta peningkatan kualitas SDM IPTEK. Kerjasama keilmuan LIPI dalam negeri meliputi kerjasama penelitian, lisensi teknologi, pengembangan, aplikasi dan komersialisasi hasil penelitian, kerjasama non-penelitian, dan konsultasi kepakaran LIPI. Sedangkan kerjasama luar negeri, LIPI melakukan joint research, workshop, pertukaran peneliti, dan beasiswa mancanegara, selain aktif menjadi anggota dan focal point di berbagai organisasi internasional. Melalui kolaborasi bersinergi, menghasilkan riset yang berkualitas, LIPI terus memberikan manfaat nyata, kontribusi berarti, dan turut mewujudkan cita dan asa membangun negeri kita tercinta, Indonesia. Berawal dari cita dan asa untuk membangun negeri, memberikan segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah Kepala LIPI, Deputi Ilmu Pengetahuan Hayati. Berawal dari cita dan asa untuk membangun negeri, memberikan segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif, dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah Kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung Iptek di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka konservasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia. Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia. Infrastruktur riset strategis. Dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi, material maju, energi, teknologi, informasi dan komunikasi, pertahanan dan keamanan, dinamika sosial, kemanusiaan dan kebudayaan, kebencanaan, inovasi teknologi dan pendayagunaan iptek, pelayanan, pengujian dan pembinaan ilmiah, serta peningkatan kualitas SDM iptek. Kerjasama keilmuan LIPI dalam negeri meliputi kerjasama penelitian, lisensi teknologi, pengembangan, aplikasi dan komersialisasi hasil penelitian, kerjasama non-penelitian, dan konsultasi kepakaran LIPI. Sedangkan kerjasama luar negeri, LIPI melakukan joint research, workshop, pertukaran peneliti, dan beasiswa mancanegara, selain aktif menjadi anggota dan focal point di berbagai organisasi internasional. Melalui kolaborasi bersinergi, menghasilkan riset yang berkualitas, LIPI terus memberikan manfaat nyata, kontribusi berarti, dan turut mewujudkan cita dan asa membangun negeri kita tercinta, Indonesia.
Are you still online?
Wah, harus segera tuh. Itu ibu rumah tangga.
Negeri memberikan segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta. Kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif, dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian, berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kimia, Deputi Ilmu Pengetahuan Teknik,
Okay, I'm very sorry because I have a trouble with my connection. Maybe after prayer, then suddenly.
Di bawah Sekretariat Utama LIPI.
Okay, now we will start, and this is, I think, the last session for this parallel session. So now is coming to Dr. Yuliati Herbani.
Yes, I'm in.
Okay. So maybe you can start for the presentation because this time is for you.
Okay.
Will you use for the recording video?
This is a recording. Yeah, please.
Okay, thank you. Okay, thank you.
Okay. Okay, committee, please play the recording.
Okay, wait a moment.
Is titled Femtosecond Laser Assist. Good afternoon, everyone. My name is Yuliati Herbani from Research Center for Physics, Indonesian Institute of Sciences. I'd like to thank to the host, Ismm 2020, for conducting this conference. Today's presentation is titled Femtosecond Laser Assisted Synthesis of Nickel-Platinum Nanoparticles at Room Temperatures. Let's begin without further ado. We know that platinum is the best catalyst for both cathode with oxygen reduction reactions and the anode with methanol oxidation reactions in fuel cell technology. It is highly desirable for reducing the amount of platinum used without compromising high activity and durability of these electrocatalysis properties. A commonly applied approach is to alloy platinum with 3D transition metals such as iron, cobalt, nickel, and copper. This picture illustrates of catalytic activity of metal platinum catalyst as Sabatier Volcano type function of platinum and oxygen binding energy. And optimal design of platinum-based catalyst should let platinum and oxygen binding energy at place at weak leg near the apex in order to balance the competition between activity and durability. And here is schematic illustration of three key factors in platinum alloy nanocatalyst design, along with the 4 type of structure architectures that partially or fully actualize these factors. Gray atoms in the inner ring represents platinum, and the blue atoms represent M nanoparticles. And here the composition, segregation, and exposed facet is the 3 key factors here considered in the design. So the most extensive explored system for platinum alloy nanoparticles is nickel platinum. We know that this nickel platinum nanoparticle synthesis usually using wet chemical method followed by annealing in high temperatures, and a laser-based synthesis is found as an alternative to produce nickel platinum alloy nanoparticles. But controlling shape is still a major challenge in the laser-based synthesis. Here is 2 examples of laser-based assisted of nickel nanoparticles and platinum nanoparticles using laser ablation and laser-induced photoreduction, respectively. And no work has been reported so far for laser-assisted synthesis of nickel alloy nanoparticles. So we work on this laser ablation and laser-induced photoreduction using a femtosecond laser. Here is the schematic diagram of the experimental setup for nickel nanoparticles. We use FAL of nickel target here immersed in pure water for 30 minutes, and for platinum nanoparticles we use flip of platinum salt solution for 15 minutes. Flip is a femtosecond laser induced photoreduction, and the resulted colloid for both nickel and platinum nanoparticles were characterized using UV spectrometers. And for the alloy nanoparticles, we use simply the same approach via these 2 schemes here, scheme 1 and scheme 2. In scheme 1, we ablated the freshly produced nickel and platinum nanoparticles in volume mixing ratio of 1:1 using a femtosecond laser for 15 minutes. And on the other hand, in the scheme 2, we ablated a nickel plate not in a pure water, but in a platinum salt solution of 0.01% for 15 minutes. And we employ UV spectrometer, TM, and XRD for the analysis of the result colloid. And the result is as below. For nickel nanoparticle, we observe a dark brown color solution with 386 nanometers. Observation peaks here indicated as a fingerprint for nickel nanoparticles, and we found some absorption for a longer wavelength was also appeared contributed from the big particles might found in this work. And for platinum nanoparticles, the more light brown color produced after laser-induced photoreduction for 15 minutes, and this is indicated by a light brown colored solution of produced platinum nanoparticles. Here we see the transparent color solution of a platinum salt changes into a light brown colored platinum nanoparticles colloid. This is validated by disappearance of these absorption peaks at 253 nanometers, light blue color here, into this kind of absorption peaks with no absorption peak, with no absorbance at a longer wavelength. So we have no aggregation is found in this platinum nanoparticle solution. And here is for the characterization result of nickel platinum alloy nanoparticles. UV spectra and TM images for both particles of scheme 1 and scheme 2 are presented here. For scheme 1, light brown color solution are produced. We observe the absorption peak at 240 nanometers and no absorptions at a longer wavelength. We found in the TM image there are spherical shaped particles with 5 to 10 nanometer size here, and for the scheme 2, on the other hand, dark brown color solution are produced and the absorption peaks at 300 to 500 white absorption peaks are observed here. And we also found from the TM image there are a core shell morphology with 25 nanometer size. And here you can see that light contrast of shell produced here. We hope this is a platinum shell are attached into the surface of nickel core inside. So for XRD characterization, the spectra indeed validated the core shell structures, where the spectra represents all the diffraction peaks from the elemental component. Here the nickel and platinum are separately found in the alloy nanoparticles. Not like the homogeneous nickel particle, nickel-platinum alloys nanoparticle, where main peaks were in between of those the elemental component and shifted to a higher theta value as the nickel content increased. And for the conclusion, we conclude that the fabrication of nickel-platinum core shell nanoparticles with 10 to 25 nanometer particle size has been successfully conducted. In this work, using a femtosecond laser ablation of nickel plate target in platinum salt solution. The core shell structure was confirmed by TM observation and XRD pattern that representing all the peaks from the elemental component of nickel and platinum separately. And on the other hand, the ablation of nickel and platinum nanoparticle mixture resulted in homogeneous alloy nanoparticles. And this work demonstrated the capability of laser-assisted method in fabrication of core shell nanoparticle which are beyond the noble metal particles. So finally, we acknowledge our Institute for Grant Research support for this work, and we also would like to thank all the authors for their contributionship. We hope this work will be continued for the further analysis of particle electrocatalysis properties. Thank you for your attention. Further feedback and discussion are all welcome. Thank you.
Thank you very much, Dr. Herbani Yuliati. Yeah, we open for discussion. If there is any question, please. Is there any question from participant? Okay, then I have several questions actually, but one question about the TM measurement, please, Dr. Yuliati Herbani.
Oh, okay.
I saw that in the TM result, there is a gray on the black circle. Hello?
Yes, yes.
Yeah.
There's a gray on the black circle, yes.
Yes, but for another, in the scheme 1, maybe, there is no such a gray color.
Yeah.
What is the, why it's happened? It's different.
Okay, so for the scheme 1, we produce homogeneous alloy nanoparticle, but in scheme 2, we can produce core shell nanoparticles. So that's why you can see in the scheme 1, there's no phase segregation in TM image.
Yeah, what then the effect, what is cause of this effect from scheme 2? why it doesn't show the homogeneous
okay.
particles.
Okay. So in the scheme one, we ablated two kind of nanoparticles, nickel and platinum nanoparticles together in one batch of in one time. So, but in the scheme two, we ablated nickel plate inside or immersed in platinum salt. So platinum salt will be reduced to platinum atoms and then deposited to the nickel atom that ablated by the laser. So that's why the two different scheme are produce a different kind of morphology of a nanoparticle.
Okay, I got the result. Yeah, and yeah, because the time is over already. Thank you very much for your nice presentation and your time for today to join for this conference.
Thank you.
Thank you. And we move to another paper. Everjoy Mones from Everjoy Mones, Miss Everjoy Mones, about the effect of PVP and reaction time to the morphology of synthesis nickel nanowires.
Okay, good afternoon, everyone. I have a submitted recorded, so
okay.
Yes, thank you very much.
Time is yours. Okay.
Good afternoon, everyone. In Filipino, magandang hapon. Also, salamat sa ore. So, I am Everjoy Mones from the Philippines, and today I will be presenting our research entitled Effect of Polyvinyl pyrrolidone, or PVP, and reaction time to the morphology of synthesized nickel nanowires. Again, I'm from the Philippines. So here is the outline of our presentation today. So I will be introducing nickel, which is the main object of our study. Then the methodology, wherein we employed a simple chemical reduction method to synthesize nickel. Then results and discussion showing the characterizations of our synthesized samples. And conclusion, and then acknowledgement. So nickel, it is a commonly known metal. In fact, in the Philippines, we have nickel reserves, and one of the largest nickel reserves in our country is Rio Tuba mine, as shown in the map or the archipelago of our country. So nickel is commonly, we know nickel is applied or used to make nickel coins. Then batteries, optimizing its conductivity. Then coating, and lastly as catalyst. So the objective of our research is to determine the effect of surfactant, specifically polyvinyl pyrrolidone, and the reaction time. So in this research, we vary the reaction time on the morphology of nickel synthesized using simple chemical reduction method. So first, we have a metal solution. Our study is divided into two. So without PVP and with PVP to determine the effects of surfactant to the surface morphology of nickel synthesized using chemical reduction method. So the solution was heated in a hot plate at 70 degrees Celsius for 15 minutes. The solutions were prepared in ethylene glycol. Hydrazine was then added to the nickel chloride metal solution and heated for 70 degrees for 10 minutes at 70 degrees Celsius. Then after 10 minutes, sodium hydroxide was added to have an OH source. Then the reaction times considered for the overall is 0.5 hour or 30 minutes, 1 hour, 2 hours, and 3 hours. So the characterization employed to understand further the sample are SEM or scanning electron microscopy and XRD or X-ray diffraction. So the figure in this slide shows the XRD pattern of nickel sample synthesized using simple chemical reduction method. So according to the XRD pattern, characteristic peaks were found to be at 2 theta is equal to 44.4 degrees, 51.9 degrees, and 76.5 degrees, which corresponds to the 111, 200, and 220 planes of face-centered cubic or FCC nickel, respectively. So this suggested the successful fabrication of metallic nickel nanowires using chemical reduction method, since characteristic peaks of nickel were found in the XRD. Next is the SEM, or the scanning electron microscopy result. So we have here the SEM images of nickel nanowires synthesized using chemical reduction method with PVP for 30 minutes, 1 hour, and 2 hours with magnifications of 20,000, 16,000, and 20,000 respectively. Then we also have the SEM images for samples synthesized without the presence of surfactant, which in this research we use PVP for 30 minutes, 1 hour, and 2 hours with magnification of 5,000. SEM images of the nickel nanowires prepared by chemical reduction method in ethylene glycol and without PVP at different reaction times is shown, just as I stated earlier. So chain-like structures were mostly observed with the addition of PVP, as can be seen here in the slide, from A to C, chain-like. Then nickel nanowire synthesized without PVP had smoother surface compared to the nanowire synthesized with PVP. So without PVP, we had a nanowire-like structure, while with PVP, we had a chain-like structure. So in this result shows that PVP encapsulated the nickel nanoparticles prior to nanowire formation, which resulted to the chain-like structure of the wires. So with PVP, there is an encapsulation of the nanoparticles. So it resulted to a chain-like compared to, on the other hand, without PVP, since there is no encapsulation, the particles stick to each other, which resulted to a nanowire-like structure. We have here the table showing the tabulated average length and diameter of nickel nanowires synthesized using chemical reduction method with and without PVP for different reaction times. So for increasing reaction time in the samples wherein the nickel nanowires were synthesized with PVP, the average length and the average diameter increases for increasing reaction time. On the other hand, for the samples without PVP, the average length increases while the average diameter decreases. So we have here the so-called idea or concept on how the nanowires were formed. So first, there is the formation of nickel nuclei. Then, the particles were arranged into chain-like morphology as time was extended. So it can be observed that as the time increases, the average length and diameter of nickel also increased, as shown here, where in the presence of PVP. So this can be attributed to Ostwald ripening. Then, due to the inherent magnetic property of the nanoparticles, formation of nanowires due to magnetic field became a possibility in our could be possible in our research. So in the initial reaction stage, the nucleation of nickel primary particles take place in the reaction solution, and then the nanoparticles are aligned along magnetic interaction. So the necessary condition for the formation of nickel wires is that the alignment of particles occur prior to the end of the reduction reaction, which can be observed both in the samples. So without PVP, nanowires were formed, nanowires-like structure were formed. Then with PVP, there was a chain-like structure or morphology rather. So to conclude our research, this presentation, nickel nanowires were successfully synthesized using chemical reduction method. Increasing the reaction time and addition of PVP resulted to longer nanowires. Then diameter of the wires increased with the presence of PVP due to the encapsulation of the formed nanoparticles with the surfactant. So thank you very much for paying attention. Maraming salamat. Terima kasih. Thank you. Here is our references. Good afternoon, everyone.
Okay, thank you very much, Ms. Iverjoy Mones, for your nice presentation. And we open for the question now. Is there any question from the participant? We open for question. If no, then I have several questions for you. We have around 4 minutes left. Yeah, you mentioned that there is an encapsulation after you give for PVP as a surfactant in your reduction of the metal of nickel. So what would you expect for your research for the next application by using this surfactant of PVP? Could you explain for us?
Can you please repeat the question, because my internet connection's a little unstable. If it's okay, I'm sorry.
You mentioned that there is an encapsulation when you use for the surfactant of PVP for your reduction of your metal, and then so then the more you give the PVP and the more you give the reaction time longer, then the encapsulation become higher in the DM, then also the size of the medium matter is also increasing, right?
Yes. Can you please type the question, because I really can't hear it clearly.
Hello.
I'm sorry. Can you please type the question in the chat box so I can see it? Unfortunately, I cannot hear the question clearly. We're having, I think, little disconnect internet problems, at least on my end, I think. I apologize for this. I'm sorry.
Hello, could you hear my voice now?
Yes, I can hear you better. Yes.
Okay. I'm sorry for my internet connection. Okay. Yes. Could you answer for my question? Because when you use the surfactant for PVP, there is encapsulation and the medium matter become larger. So what do you want to expect for the application when you use for the surfactant?
one of the purpose of the surfactant, aside from the encapsulation of the nickel nanoparticles to form a chain-like structure, is to provide or rather aid the stabilization of the formation of the nickel nanoparticles. So by the stabilization of the formation of the nickel nanoparticles, the stabilization comes when the PVP encapsulates the nickel. So by encapsulating the nickel nanoparticles, or by rather incorporating PVP, maybe we can explore the possible applications in the electronics aside from the nanowires, wherein nanowire-like structure rather without the application of PVP. So it would be interesting, I believe, in our research if we expand it further by exploring its application in electronics, by by applying our sample maybe on a film or a glass, then measure its heat resistance. So we can determine the difference. What would be the heat resistance without PVP and with PVP? So I hope I answered your question, ma'am.
Okay. Yeah. I get your answer. Okay, because the time is already over, so we will move to another paper, another participant. Thank you, Miss Verjoy. And yeah, I know several Philippine words, sentence, because I have a lot of friends, good friend there, like payung, putih, and something like that. So I think it's the same with Indonesian language, right? Okay, see you next time. And yeah, we will move to another.
Yes, thank you very much.
Yeah, paper. So we will go to Kirana Putri.
Yes, I'm here.
Okay. So the time is yours. Please start for your presentation.
Okay, I think I have sent my file, my presentation file. So can you play it for me? Thank you.
Okay, the committee will open.
Okay, thank you. Next one.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. First, I would like to thank the committee of the 4th International Seminar on Metallurgy and Materials for the chance to present my work in this seminar. Before starting my presentation, please allow me to introduce myself. My name is Kirana Yuniati Putri from Departemen Fisika, Universitas Indonesia. I am also a junior researcher in Research Center for Physics, Indonesian Institute of Sciences. The work that I will be presenting here is entitled LSPR Evaluation Using Boundary Element Method to Determine the Size Evolution of Triangular Gold Nanoparticles. This is the outline of my presentation, starting from introduction, followed by methodology, result and its discussion, and ending with conclusion. Let me start with introducing the unique optical property of gold nanoparticles, namely localized surface plasma resonance or LSPR. Gold nanoparticles possess an abundant amount of conductive electrons. These electrons are easily polarized by the electric field of incoming light. As a result, collective oscillations or plasmons are generated. Since plasmon of gold nanoparticles are non-propagating excitations and distributed over the particle volume, they are referred to as localized surface plasmons. To excite these plasmons, the frequency of the incoming light should be in resonance with oscillations. Consequently, the color displayed by colloidal gold solution is dependent on its extinction wavelength. There are several factors that affect the LSPR of gold nanoparticles, such as the dielectric surroundings, physical-chemical environments, composition, assembly, and morphology. Dielectric surroundings, physical-chemical environments, and assembly of gold nanoparticles influence their interparticle distance. Meanwhile, changes in composition and morphology of gold nanoparticles are reflected by their size, shape, and architecture. To understand the optical behavior of gold nanoparticles, we can use numerical calculation or simulation. One of the popular and efficient approaches is the boundary element method or BEM. In this method, the nanoparticles and the medium are defined as dielectric bodies which are separated by clear interfaces. Each body has homogeneous and isotropic dielectric property. As you can see in the illustration, in case of single nanoparticle, we only need to define the dielectric property of the medium and the nanoparticle, along with the nanoparticle shape and size. In case of two particles or more, we need to define the dielectric property for each particles and the medium. And in case of layered particles, we need to define morphology of the nanoparticles, the dielectric property, the thickness of each layer, also the dielectric property of the medium. Recently, anisotropic gold nanoparticles have drawn much attention due to their promising applications in various areas. Nanoparticles with LSPR in the near-infrared region, such as triangular gold nanoparticles, have potential use in cancer therapy, biological assays, and cell imaging. The LSPR of triangular gold nanoparticles is also highly sensitive to the changes of their morphology and surrounding mediums, making them suitable for sensing. This increased attention has resulted in the development of various synthesis approaches to obtain the triangular gold nanoparticles. Highly monodispersed triangular gold nanoparticles have been synthesized using templating method. They are also often found in the products of biosynthesis. However, chemical synthesis is still the most used method to produce triangular gold nanoparticles. It usually involves kinetic control or addition of shape-directing agents. Triangular gold nanoparticles are usually formed in low kinetic rates. In developing a method to synthesize triangular gold nanotriangles, it is essential to understand their growth process. However, characterization is usually done after the synthesis process has finished. It is very difficult to take a sample of nanoparticles in the middle of synthesis without disturbing the process. Therefore, the challenge is how to observe the growth of triangular gold nanoparticles during synthesis without disturbing the process. To answer this question, we propose PEM simulation as a means to study the size evolution of triangular gold nanoparticles during synthesis. Specifically, we aim to study the effect of gold nanotriangle size on the LSPR using MNP-BEM and use the simulation result to estimate the size of triangular gold nanoparticles at certain times during synthesis period. In performing the numerical calculation using MNP-BEM, we follow the steps described in the figure. At first, we define the particle shape as a triangle and set the aspect ratio as the variable parameter. Aspect ratio is defined as the length of the nanotriangle divided by its thickness. We also define the dielectric function of particles as gold and medium as water. And then we set up a comparticle object. This object contains descriptions on how the particle is embedded in the dielectric environment. Once the comparticle object is ready, we can call a solver for boundary element method equations given by the toolbox. In this work, we use the quasi-static approach since this is the most efficient approach. Before starting the calculation, we should define the condition for incoming light, such as the wavelength and polarization. After the calculation has finished, we can get the extinction cross-section for its wavelength and polarization. For the synthesis of triangular gold nanoparticles, we follow the method used by Tengayes et al. with several modifications. As illustrated, we focused a femtosecond laser beam into the precursor solution. After 5-second irradiation, hydrogen peroxide was added, and the sample was left for 24 hours. During the aging process, the extinction was monitored every hour using UV spectrophotometer. Later, the recorded extinction spectra will be analyzed as a function of time. This is the result of the numerical calculation using MNPBM. As you can see, a unique feature of triangular cold nanoparticle can be seen here, which is the appearance of a solder on the side of the main extinction peak. Different from nanorod, it is not separated from the main peak. Interestingly, the position of the shoulder is different when the light polarization changes. The simulation also shows that as the aspect ratio increases, the extinction peak shifts to the right. By fitting the data, we can see that the extinction peak wavelength correlates exponentially to the aspect ratio of the nanotriangles. The fitted curve for Y polarization was somehow lower, but the trend of the LSPR shifts is similar. It is also indicated that the thickness of nanotriangles did not change the extinction peak wavelength significantly. This is the recorded extinction spectra during the synthesis of triangular cold nanoparticles. Each spectrum has two distinct peaks. The right peak corresponds to the nanotriangle, and the left one is the sign of nanospares as byproducts. The right peak showed the unique feature of a cold nanotriangle, which is the appearance of a shoulder to the side of the main peak. By normalizing the spectra, the peak wavelength shift can be observed in detail. As time passes, the nanotriangle peak shifts to the right, while the peak wavelength of the nanosphere is relatively constant. This indicates the size evolution of nanotriangles and the unchanging size of nanospheres. Using the exponential correlation from the simulation study, the aspect ratio of the triangular cold nanoparticles from the experiment was calculated based on their extinction peak wavelength. The result is summarized in this table. The estimated aspect ratio here is most probably the dominant value and not necessarily the average value. By plotting the aspect ratio to the synthesis time, it is predicted that the triangular cold nanoparticles grow fast in the early hours and slow down towards the end. To conclude my presentation, there are several things that can be highlighted. First is that the simulation study using MNPBM has shown that the extinction peak wavelength of triangular cold nanoparticles is exponentially correlated to the aspect ratio. And using the result of the simulation, the triangular cold nanoparticles are predicted to grow fast during the early stages and slow down toward the ends. Finally, BEM simulation can be considered as a potential tool for studying the growth or decay of anisotropic nanoparticles. And that brings us to the end of my presentation. Thanks for your attention. Thank you for listening. Please feel free to give me any question or comments.
Hello. Okay, thank you very much.
Hello?
Yeah, thank you very much for your presentation, nice presentation for this session. Hello.
Sorry, I can't really hear you.
Can you hear my voice now?
Hello?
Hello.
Okay, I think it's better. Yes, it's better now. Yes, I think it's better now.
Hello?
I can hear you already. Yes, hello?
Hello, can you hear my voice now?
Yes, I can. Hello? Hello?
Halo Bu Murni, are you still online? I think Bu Murni have a Internet connection problem.
I think it's because of the rain.
Hello, hello.
Hello?
Halo, ya Bu Murni.
Yeah, I'm very sorry because I use my headset. Then it's showing directly for the connection when I speak, and maybe there is a problem with my headset. Okay, thank you very much for your nice presentation. I open for the question in this session. Is there any question from the participant? If not, then I would like to ask you about the you are doing also for the experiment to confirm for the simulation, right?
Yes.
Using
I think
using femtosecond laser assisted AU
yes.
particle in the triangle shape. Yes. So you mentioned that it's growing faster in the first step, then after that it goes down after in the last step actually for your experiment. Could you explain why it's happened? What is the mechanism inside when you do for the experiment? Why it like that?
Okay. Thank you for the question. So actually, at first, I irradiate the sample, the precursor solution containing the gold salt solution with the laser for about 5 seconds. At that time, during the irradiation, when the laser beam interact with the water as a solvent, it will, it will result in the generation of electron. As you know that electron is the strong reducing agent, we can say like that. So the electron reduce the gold ions into gold atom and then later into gold nanoparticles. So at that time, during the irradiation process, we not only generate the electron but also the other products of hydrolysis, and it will result in the generation of hydrogen peroxide actually. After the irradiation is finished, so only 5 seconds, there will be no electron. There will be only hydrogen peroxide. As you can see, as you know that hydrogen peroxide is not as strong as the electron for the reducing process. So it will give slower reducing process during the later time, something like that. So that's why at the earlier stage it will give a very strong, not very fast kinetic rate because the presence of electron, and then later because the presence of a large amount of hydrogen peroxide, and later it will, of course, it will decrease the kinetic rates because the number of gold ion is there's no more gold ions there, or because the hydrogen peroxide is already been used for the reaction. And that's the
okay, I got the answer.
Process.
Okay, thank you very much. Okay, thank you very much for I think the time is up already, and we will move to another paper, another presentation. Thank you, Ms. Kirana. Yeah, now we are going to the paper of Michael Joy Alvarez. Are you here? Okay. Do you use for the recording lecture or you will give a live presentation? Hello? Hello?
Hello.
Yes.
I submitted my
Okay.
yeah.
Okay.
Yeah, there.
Okay.
Sorry. Hello, good afternoon. Okay.
I'm
Good
Michael
afternoon.
Cruz
Yes.
Alvarez from the Philippines.
It will start, I think, your lecture.
On the antibacterial.
Hello, good afternoon, everyone. So I'm Michael Cruz Alvarez from the Philippines, and I'll be presenting our study And I hope you'll enjoy this. Thank you.
Good day, everyone. I'm Michael Jose Alvarez from the Philippines, and I'll be presenting the study on the antibacterial activity of lemon juice absorbed bentonite. The outline of my presentation includes introduction, methodology, results and discussion, conclusion, references, and acknowledgement. Introduction. Clay minerals are utilized in various applications because of their abundance and absorption properties. Bentonite, an abundant and low-cost clay with montmorillonite content from the smectite group, is known to absorb and retain water. The absorption property of bentonite is employed by several studies to develop antibacterial materials with bentonite as substrate by incorporating materials with antibacterial properties. Lemon is a well-known citrus fruit used mostly in culinary and medicinal applications. Lemon consists of alkaloid compounds that pave the way to its use as a preservative and antimicrobial agent. Citric acid is abundant in lemon and is antimicrobial. The antibacterial property of lemon was investigated by numerous studies against gram-positive and gram-negative strains of bacteria. The study aims to fabricate an all-natural sample made of bentonite and lemon juice and to determine the antibacterial indices of the prepared samples against Escherichia coli and Staphylococcus aureus. Escherichia coli, or E. coli, is a gram-negative bacteria and can cause diarrhea. Staphylococcus aureus, or S. aureus, on the other hand, is a gram-positive bacteria and is known to cause skin infections. Methodology. The bentonite microscopy. These samples were pelletized with a constant diameter of 6 mm prior to agar disc diffusion. Agar disc diffusion was performed on the pelletized samples to determine their antibacterial indices against Escherichia coli and Staphylococcus aureus. The agar disc diffusion done on the samples was performed in the Natural Science Research Institute in the University of the Philippines, Diliman. From the 24-hour-old culture of the test organisms, E. coli and S. aureus, microbial suspensions of each were prepared. The pre-poured nutrient agar plates were incubated at 35 degrees Celsius and observations were made after 24 hours. Results and discussion. The figure shown on the slide is the FTIR spectrum of the prepared lemon juice absorbed bentonite. Bands from the wave numbers 3,550 per centimeters to 4,000 per centimeters was related to the hydroxyl groups of bentonite. The peaks found in between 2,900 per centimeters to 3,600 per centimeters suggests a presence of carboxyl groups that are abundant in citrus fruits. The presence of carboxyl groups proves the presence of the citric acid in the sample. The figure shown on the slide shows the surface morphologies of pristine bentonite powders and lemon juice absorbed bentonite powders at different magnifications. Agglomeration of the powders can be observed upon the incorporation of lemon juice and bentonite. This can indicate that the lemon juice was successfully included in the bentonite matrix, which can be attributed to the absorption property of bentonite. The antibacterial activity of the modified bentonite pellets was determined using agar disc diffusion. The samples were tested against E. coli and S. aureus. The clearing zones of the samples against the two strains of bacteria, as shown on this slide, were measured and the average clearing zones in each strain of bacteria were calculated to determine the antibacterial indices of the sample against each strain of bacteria. The table on this slide shows the antibacterial indices of the modified bentonite pellets for E. coli and S. aureus. Bentonite is known to have no antibacterial activity. The modified bentonite pellets have antibacterial indices of 1.4 and 1.9 against E. coli and S. aureus respectively. The antibacterial indices of the lemon juice absorbed bentonite indicate that the lemon juice was successfully incorporated in the bentonite matrix. Lemon juice consists of bioactive compounds such as flavonoids that can inhibit the growth of bacteria by altering the nature of the bacterial cell proteins and damage the cell membranes of bacteria. In addition, citric acid is able to decrease the pH level within cells. This can contribute to the death of microorganisms caused by damage to the necessary functions of the microorganism. The sample tested against S. aureus has a higher antibacterial index compared with the antibacterial index against E. coli. Based on the result, the antibacterial index of S. aureus is higher compared to the antibacterial index of E. coli. The difference in the antibacterial indices can be attributed to the difference in the structure of the cell walls of the two bacteria. S. aureus has a simpler and thinner cell wall compared to E. coli. It is possible that the peptidoglycan layer found in gram-positive bacteria such as S. aureus enables the penetration of antibacterial materials. In conclusion, lemon juice was successfully incorporated in bentonite powder by immersing the bentonite in lemon juice. Changes in the surface morphology were observed in the SEM results after the incorporation of lemon juice in the bentonite matrix, which can be attributed to the absorption property of bentonite. The FTIR spectrum of the sample suggested the presence of bentonite and lemon juice. Lastly, the antibacterial activity of the lemon juice absorbed bentonite exhibited a higher antibacterial index against S. aureus than E. coli. Incorporation of lemon juice in bentonite modified the antibacterial properties of bentonite, which can be used as a natural-based product for biomedical applications. Here are the references used from this presentation.
Okay,
The authors
thank
would
you
like
very
to
much
express their
yes,
gratitude
for your nice
to Mr.
presentation,
Luigi
Michael
Lacona
Ju
from
Alvarez.
the
Yeah, there is a question here from Dr. Andri to you. What kind of biomedical application it can be used?
One of the possible biomedical application could be it could be used for wound healing, since we tested the bentonite, the lemon juice absorbed bentonite sample to Staphylococcus aureus, which is a common bacteria that exists in wounds, in skin infections and the likes. Yeah.
Okay. Okay. Is there another question from other participant? If not, there is still around 5 minutes left, or 4 minutes until 5 minutes left, and I have a question for you. I think in the lemon juice, I think there are several or many compounds. Did you measure using like HPLC or other method to know what kind of the compound have the most big influence for your samples when the like ascorbic inside of the lemon juice? I know like there is ascorbic acid and another one. So can you explain what is the most compound do you know for this?
Actually, the basis for the contents of lemon was based entirely on the references that we got. So prior to the question, if we were able to identify the other components, we did not, because basically the contents of the lemon are entirely based on the references we got. Yeah.
Yeah, because when you use the pristine of bentonite and without the lemon citrus, it will give effect so much, right, for your antibacterials. So then next, what do you expect for the next research from you using this citrus or lemon juice for your samples?
I'm sorry. Can you repeat the question? I was not able to understand it entirely. Sorry.
Yeah. I think in your slide there is a big difference when you use the pristine bentonite and also when you use for the lemon juice and absorb in the bentonite, right?
Okay.
Yeah, in the antibacterial effect. So for
perhaps the samples can be applied in other types of bacteria or perhaps in antifungal applications. That would do perhaps, yeah.
Is there any reference do you read for this before, or is there any other work related to your research?
Yeah, we actually do have references, and as the person that I've mentioned that it could be applied in other types of bacteria, antifungal application could be done for future work because there's no there's a lack of work on that matter. Yeah.
Okay.
Thank you.
Thank you very much. And the time I think is already up, and thank you for your nice presentation.
Thank you so much.
And we will move to another paper now. I think this is the last paper, or this is the last paper after you. Thank you very much.
Thank you so
Mr.
much.
Mikael Joy Alvarez. The paper from Nurhayati Indah Ciptasari about synthesis of graphite oxide using hammer method, oxidation time influence. Hello.
Yeah, hello.
Yeah.
Yeah, hello.
Yeah, okay. Ms. Nurhayati Indah Ciptasari, would you like to use recording video or live presentation?
Recording video.
Okay.
Assalamualaikum warahmatullahi wabarakatuh. Good evening, ladies and gentlemen. Introducing, I am Nurhayati Indah Ciptasari from the Center for Metallurgy and Materials LIPI, and currently I am also a doctoral student at the University of Indonesia. On this occasion, I will present my paper about synthesis of graphite oxide using Hammer's method, oxidation time influence. We know the development of renewable and sustainable energy has generated increased attention in recent years. Studies on lithium-ion batteries for cellular application is one of those ongoing. But there are different materials that are often investigated to enhance performance as electrode materials and are quite promising, namely graphene. Graphene is a two-dimensional crystal as thick as a single atom from a hexagonal lattice-bound carbon atom sp2 with outstanding physical properties. Not only has a wide specific surface area, but also high intrinsic mobility, high modulation, high thermal conductivity, high electrical conductivity, and optical transmission. A lot of graphene application from hydrogen storage system to batteries. Graphene being used in electronics became possible as that can make transistor consume less energy and dissipate heat more efficiently than those based on silicon. Some other graphene uses include manufacturing chemical sensor and transparent conduction film for solar cell and liquid crystal devices. Additionally, a high graphene surface to mass ratio makes this suitable for ultracapacitor and battery. Graphene synthesis method include mechanical exfoliation, graphene oxide reduction, and chemical vapor deposition. Before graphite oxide reduction becomes graphene oxide, graphite must be produced through the graphite oxidation. Fig 2 shows scheme of graphite oxidation using Saunden-Meyer method with subsequent thermal exfoliation using higher excess of the oxidizing agent and additive of concentrated sulfuric acid. This modification enabled to carry out continuous process without the necessity of nitric acid addition during the reaction. But this method was still too long till Hammer proposed in 1958 graphite oxidation using potassium permanganate and sodium nitrite in concentrated sulfuric acid that shortened oxidation time to several hours. The hammer method is the most commonly used method for processing graphene oxide, as it provides high efficiency and safety in reaction. The hammer method is used producing graphene by oxidizing graphite to graphene oxide by using suitable oxidizing agents such as potassium permanganate. The modified Hammer's method introduces a way to get a more stable graphene oxide colloidal solution. The graphene oxide so produced is again then chemically reduced to get graphene. The objective of this research is to produce graphite oxide powder as a precursor for synthesizing of graphene oxide with a variation in oxidation time using the Hammer method. Material and method. Graphite oxide was synthesized using the Hammer method as depicted in the previous method. The material used are pure graphite powder, sulfuric acid, potassium permanganate, sodium nitrate, hydrogen peroxide, ice, and distilled water. In this method, 1.5 gram of sodium nitrate dissolved with 75 ml sulfuric acid in an ice bath for several minutes. Then 7.5 gram of potassium permanganate and 1.5 gram of graphite was added into mixing solution under stirring condition for 2 hours at temperature below 20 degrees Celsius. Permanganate, one of the strong oxidants, is expected to increase graphite oxidation, especially in acidic media. After that, remove from the ice bath with the temperature set at 37 degrees Celsius and stir for 12, 16, and 24 hours. Furthermore, add 125 ml of distilled water, followed by addition of 10 ml of hydrogen peroxide 30% and 400 ml of distilled water until the solution changes color from dark brown into yellow. The addition of hydrogen peroxide eliminates the remaining permanganate and reduces manganese dioxide into insoluble manganese sulfate so that the color changes from dark brown into yellow. Next, the solution was washed with 1 molar chloric acid and distilled water until the pH became neutral. Finally, the solution was centrifuged at 8000 rpm for 15 minutes and dried in oven at 80 degrees Celsius for 16 hours. Graphite oxide powder was characterized using SEM and XRD. The X-ray diffraction investigation carried out at an angle of equal 5 degree until 90 degree with lambda juga alpha 1.541 Armstrong resulted in a peak of graphite and graphite oxide material. On figure 1, the graphite intensity is most lower. It indicates that graphite is oxidized to form oxide graphite. This is in line with the observation of previous studies wherein peak of graphite and graphite oxide pattern at 26.2 degree and 9 till 12 degree corresponding to a layer-to-layer descent of 0.88 nanometer more or less, which is close to the literature. In order to determine a comparison of X-ray pattern with oxidation time variation in graphite oxide, the X-ray graph is plotted in figure 2. That as with the oxidation time, there are differences in peaks and intensity at 2 theta angle. The amount of X-ray intensity was determined by the material crystallinity. The higher the crystallinity rate, the more orderly the substance atom organized. With more regular arrangement of atoms, electrons will be easier to move, thus increasing the advantage of the material's electrical conductivity. Calculating the distance between layers, the spacing called Use-Breaks law, which aims to analyze the effect of oxidation time on the interlayer distance ratio. And Table 1 presents the result of the calculation of the distance between layers in comparison to the spacing is graphite and graphite oxide. Based on the Table 1, it can be seen that the distance of the layer from graphite to graphite oxide is increasing. It's caused by the formation of functional oxidant group to the oxidized graphite and increases in the water content when the graphite oxide is formed. Same result. Figure 5 shows the graphite oxide surface morphology with different oxidation time variation at magnification of 10,000. Sample thickness morphology is uneven and overlaps. The surface morphology of the thinner graphite oxide is slightly tempered under oxidation time condition of 20 hours. It's because the sample result contain oxygen functional groups. As the reaction time increases, the quantity of functional oxygen group decreases. Result of the elemental analysis obtained from index in Figure 6 show that most of the compound content is carbon with a mass of 66.55% and followed by oxygen with a mass of 28.88%, which prove graphite oxide formation. The presence of elements of sulfur, potassium, and manganese, as seen in Table 2, may be due to incomplete oxidation. Another aspect is the possibility for impurities that derive from the raw material used. Because the electrodes used in this experiment are pure graphite, the electrodes may be presumed not to be pure carbon. It contains impurities therein and will affect the final analysis result. As is even before the oxidation process, the electrodes themselves may contain sulfur. Conclusion. In this work, graphite oxide has been successfully synthesized using Hammer's method. Graphite oxide is obtained by oxidizing of graphite using potassium permanganate as an oxidizer, which is identified by a dark brown color change in the solution. The characterization of the result was done by using XRD and SEM-IDS. Research results show that better graphite oxide are obtained with an oxidation time of 20 hours, so that the process is expected to be a raw material further for producing graphene. Finally, the author would like to thank the Ministry of Science and Technology for Scientech Scholarship, Funding Putih 2020 from University of Indonesia, and Research Center for Metallurgy and Material, Indonesian Institute of Sciences. Thank you.
Okay, thank you very much for your presentation, Ms. Nurhayati Indah Ciptasari. And I open for question. If there is any question, Dr. Andri Hardiansyah, please.
Okay, and I have one question.
Okay, the time is
Yeah,
yours, please.
actually two questions.
Yes.
The first one is
There is 4 minutes left, so I think it's
okay. The oxidation time, yeah. Why you expected that the 20 hours maybe the best oxidation time, because I see in the interlayer spacing distance there is no significant difference between its time for oxidation. I mean the interlayer spacing distance still in the 8 nanometer. That's the first question, and then the second question. Your EDS results still consist of sulfur and then potassium and then manganese that I expect it's still exists on your samples. Then I want to ask about the purification or washing procedure in your synthesized procedure. Thank you.
Okay, thank you, Dr. Andri. So,
Sorry, can repeat question? My signal unstable in here.
Okay.
Sorry.
Okay. Why the 20 hours of oxidation you choose as the best oxidation time for your graphene oxide synthesis?
Yes.
Yes. And then the second, how you do the purification and washing the graphene oxide? Because I see your EDS results still consist of sulfur, potassium, and manganese.
My purification with sorry. Purification with HCl and hydrogen peroxide. My leaching with sulfuric acid, potassium permanganate, and sodium nitrate. Okay, that's
and then are you using the distilled water or?
Yes.
The impurities?
Yes. Yeah, I will. I use my distilled water, but my pH until 5 because distilled water is not good. So stay at 5.
Okay.
Not neutral.
Okay. And how many times?
Hello?
Are you using centrifugation?
Hello.
How many times?
Hello.
Yes.
Yes.
Yes. How about
sorry?
Yes. How about the first question? Why you choose 20 hours as the best oxidation time?
Sorry.
Oh, okay. Maybe I will write. Okay.
Yeah. Yes. You can write. Sorry. No signal is not good.
Is it
Maybe
okay
it's rain.
if I have for the answer for this?
Yes, of course.
Maybe this is because the last. Maybe things we can discuss further with you. It's very interesting.
Yes.
Because I think we are very close each other with our work.
Okay.
Dr.
Thank
Andrea, for the first I saw for the presentation slide of Miss Nurhayati Indah, I can catch what is the result. Yeah, obtained from the screen time. 20 hours is the best for her because I think she mentioned about the XRD result and also SEM. Yeah, this is actually for the result we have to still confirm using the TM and also Raman spectroscopy because this is I think the most powerful result. If we can get from the Raman to know the defect of the layers when we give the larger time for the oxidation, because then also for the IG and ID, then the ratio also the Raman I think is the most powerful. And also for her, I see that the because the XRD for the despacing is I think is higher in the 20 minutes, 20 hours. I mean, I'm sorry. And also for the SEM result, because this is I think the for the graphene we have to use like very high magnification, right? But here I think the 10,000 is already not good enough, so we have to use the TM and also another methods. And for the second one, for the purification, yes, actually yes, if there is still acid condition for the result, there is a sulfur still and also for oxidate permanganate. Yeah, for this, when we realized that in our lab there is a distilled water and we measure for pH, it's around 5. So it's very difficult then for us to get the neutral solution. We bought this from the commercially available of the distilled water from outside, and it's already very good actually, but I don't know why this is in still acid condition. And also for the permanganate or Cayman 4, so yes, it's still contained inside of the sample, so we have to do purification again actually. Using, we did also many times for centrifugation, but I think to have the complete purification, we have to do it again. Thank you very much for your comment and give very good suggestion for us.
Yes, you are welcome.
Okay, no, I think it's the time for closing. So I'm very happy that our audience still here. And actually there is one paper left, but from Miss Latifa Isna, but I think she didn't come to our conference, so I think we have to leave soon because the time also is already up. So then we will have the closing ceremony. Then I thank you very much for all audience to attend for this conference, and I hope this conference will be very beneficial for us to have like a very good collaboration and very good discussion to give insight of many knowledge to our next in the future for our work and research. Then thank you very much, and thank you very much. And I'm very sorry if I'm as a moderator here if there is a mistake for this session, for this parallel session. I would like to have apologies from you, and I give to the committee to do the closing from the chairman of the Ismm 2020. Thank you so much.
Okay, thank you, Bu Murni. We will do some closing. There is some video from the chief of conference, and then in the last session we have to some photo session. So I hope all participants can turn on the camera.
Hello everyone, I am Denny. In here I speak as co-chair of the 4th ISMM. I would deliver a great thank you for your joining and contribution to our event. Indeed, during these 2 days, discussions are very insightful and giving such know-how exchange to all of us in area of material and metallurgy. We hope that this event will continue and have an impact on research collaboration or other positive impact. Before closing, let me tell you about our future conference, that is ISFAP 2021, or the 6th International Symposium on Frontier of Applied Physics. This conference still is our collaboration conference and soon will be announced through our website. Finally, I will address again a sincere thanks to all of you. And the 4th ISMM is officially closed, and hope we will meet again in the next year in the ISFAP event with more diverse and insightful research results. Hello everyone, I am Denny. In here I...
Okay, we will do some photo session. Please turn on your camera, all participants. Mr. Mukhlis, can you help to take the photo? And Mr. Eddie?
Okay, everyone, please be ready.
Screenshotnya pakai apa sih?
Still not all attendants turn on the camera. We wait other attendants. Okay, we will take a picture now. Okay, 1, 2, 3. Okay, finish. Thank you.
Okay, thank you for all participants who joined this conference. See you in the next conference. Thank you so much.
Thank you, everyone.
Thank you.
Stay healthy.
See you next time.
Yeah. See you next year.
Enggak, enggak. Yuk.